Hello everyone. Am I audible?
Yes, sir. Good evening, sir.
Very good evening. So, hello. This will be my first session for this course. Let me first introduce myself. I'm Pulkit Mangal. I'm from Rajasthan, and I will be the course TA for this term for this new Intro to DLGNI course. And I joined this degree in the September 22 term. I am currently in the degree level of the program, and beside the DLGNI, I have been the TA for Maths 2, MLT, and MLP before. And currently, I'm working as an intern in IITM Research Park along with this TA-ship. So that's a small intro about me. Uh, yeah. Now, for the today's session, the agenda is to. Uh, Thank you. For today's session, the agenda is to discuss the week two theory part first, and then time permits, we will discuss the implementation also. Otherwise, Puneet will do it in the next session. Okay. So yes, any doubt?
Okay, sir. So, week one we are doing or week two?
Week one, I think it's already done, right? If you have any doubt, I can take that first.
Okay, sir.
If anybody else also has any doubt regarding week one, then we can take that first. Else we'll move on to week two.
Sir, can you hear me? Hello, sir, can you hear me?
Yeah, I can hear you, but whoever is speaking, his voice is very low.
Okay, sir, is it better now?
Yeah, it is better now.
Okay, sir, actually, week one has been covered, but I feel that theoretical part was not covered really. I mean, it wasn't covered well. So, because I was
So I
looking at
will
the.
do a little recap of whatever happened in week one today. Okay. It
Okay,
won't be
sir.
fully detailed, but I will do a little recap before starting with week two. Yeah. Daksh, about
Okay,
the
sir.
uh, Daksh, about the project, I do not have much information for the project. I think you can either post it in the Discourse forum, or maybe you can contact Jimmy sir. I think he is handling the project related things, or Anamika ma'am. Okay. So anyone else has any other doubt?
Excuse me, sir. Hello.
Yeah. Hello.
Yes, sir.
Yeah. Yes, sir.
So I'm asking for we have 2 weeks. These assignments and all videos are uploaded, lectures
Mm,
uploaded.
mm.
So I'm seeing that there's a lot of lectures. Like
Yeah.
is it possible?
Yeah, yeah, I totally get your point there. I think in the 2 weeks only we have 43 videos.
So, any we are conducting live session and all. So is there any single 2 3 videos like that can cover everything? Like we have to watch all these things. Like I'm just
See, I'm not sure what was covered in the last three sessions. One was taken by Puneet on Tuesday, another, I think, one by Levin sir, and
So, first there was
Mm.
a coding session. Levin sir also took, I think, coding session.
yeah, and I
Uh,
think
and
science took
on
the
Saturday,
theory.
there was a theory session on week one.
Yeah, so I'm not sure how depth they have covered, but maybe you can look at
Mm.
those.
And Okay, and I'm also not getting any notification regarding DL session. Like for TDS, I'm getting the email that today you have TDS session this and that time. For DL, I missed like so many classes previously. Like
You can add it on. Have you added the calendar?
yes, I've added in the calendar, but like why
Then
I'm not
it
getting?
you will not get the mail regarding
Huh,
the
yeah,
event, but you should get a notification from the Google Calendar itself
yeah. In
if you have
Google
turned it on.
Calendar, I manually checked and it says that 2:30 to 4:30 p.m. So is
Uh,
there any session happened at that time?
no, no, no. Then I think your timing for the Google Calendar is different.
So
Check the in the.
actually, the
Hmm.
calendar given in the course portal is different. I mean, there are two parallel calendars showing in a calendar. There is a mismatch like that. Another calendar which Avril is mentioning is actually that class, and it's also showing 8 a.m. classes in the morning. So there are
Uh,
two calendars
Yes,
existing.
one like I want to excuse me, ma'am. Like one email was given about the calendar. That is the original one. If you follow it, you will get it.
okay, I will ask the course team to rectify that. I will ask them to remove the other calendar. Okay.
So how will we get to know like
Uh,
which calendar is on?
the one that you got from the mail. Okay, must have got on mail on I think the last Tuesday. Because at that
I
time
got
the yeah, use that calendar. Okay.
okay, sir.
Yeah. Any other issue? Okay, then let's start. First, we will do a little bit recap on whatever was covered in the week one. Yes, Priyanshu.
Sir, given this course has been introduced first time in diploma, so I wanted to check whether the content have been taken from the degree course or is this design
No, no, no.
new?
It's not taken from the degree course. It's been redesigned. Okay. It's totally new content. Yeah, of course, the things will be like similar. You are studying the things like Macaulay-Pitts neuron, perceptron, backpropagation, all of these things you will be, of course, be studying in the uh, DL course that is there in the degree level, but there it will be much deeper, and of course, the lectures and all will be different.
Okay, sir.
Okay,
Thank you.
and here we'll be studying it not in that much detail. Yes, Anshuman, any doubt?
Yeah, so I hope I'm audible.
Yes, there.
I have a doubt quite related to that.
Hmm.
That since this is a new course and I have taken the project along with it, and I
Okay.
know nothing about deep learning. So, what would you suggest to complete the course earlier? Because project deadlines are earlier than the course deadlines.
Mhm. Yeah. Okay. So for the project part, mm, you have to search for any online resources regarding the fine tuning one because I think the project is about fine tuning a old model. So you may find many resources online regarding fine tuning. You can watch that. Okay. For the theory part, I think Levin sir has suggested one book. You can try going through that. Okay. Else, other book if you want, you can take a look at the deep learning book by Goodfellow or maybe by PRML by Bishop. Okay. Those book also you can refer if you want.
Okay, thank you, sir.
Yes, Shubham.
So like today you will cover with the week two one, means like the week two part
Week
or
one,
week.
a little bit recap. We will start and then we will
Okay,
move on to the week two theory. And if
okay, fine.
time left, then we will move on to the implementation. As Puneet will do it in the next session. Okay.
Like sir, one more doubt I have. Like in the instructor session, which was
Mm,
being held like the before, there was
mm.
one part that like I cannot understand the like why with the help of sigmoid function we are able to reduce the like transform from linear separability to non-linear separability. That part.
Okay. Uh, let's see if we can do that today. Yes, Aditya.
Okay, sir, my doubt was regarding the graded assignment.
Okay.
So, sir, when I had asked one of the instructors about this assignment case, so they
Mm.
told me that for this specific course, the deadline and the release of the assignments would be from Wednesday to Wednesday. That
Yes.
means it got released on Wednesday, deadline on Wednesday, and on the same Wednesday, we get the assignment for the next week and so on.
Yeah.
Okay.
Because the
But
assignments, the questions are being made. all the things are in the process.
Exactly, sir. But sir, now if we head over to the course portal, it says that the deadline for the first assignment is the 5th. So, sir, my question was that in the other courses, other diploma level courses, for example, I've also taken PDSA,
Hmm.
the assignments which have the deadline set for 5th of this month have
They have
the
also assignments for
assignments
week
for
2.
week. Yes, sir, exactly. So, sir, how would it be for this course?
See, for those, the week 2 assignment is already released, but for this course, the week 2 assignment has not released yet, right?
Yes,
So
sir,
I
that's
don't
right.
think so they will share it for the 5 October itself because it is just 5 days ahead. So at least I think you will get 10 days gap, I think. Okay, so don't worry about that part.
Okay, sir. So that's nothing to worry about, right?
Yeah,
Okay, sir.
don't
Great.
worry.
That's what I wanted
Okay.
to ask. Thank you.
Yes, Karthikeyan. Okay. Yeah, any more doubt? Yes, Priyanshu.
Sir, are you going to take any mentor sessions as well? I mean, as of now, we have not received any
I
information.
don't think so. We will be having any mentor sessions for the DLGNI course. I'm not sure if it will happen. You will get the form regarding that.
Okay, sir.
Pulkit,
Yeah.
this is Karthikeyan.
Yeah.
Who pasted this timing for this course in the chat? Because for me, I added the TA sessions are okay, 8 to 10 and 9 to 11. But the instructor session, in my calendar, it shows 8 to 9 for both Fridays and Saturday. It shows 8 to 9 instead of 9 to 10 and 9.
I think he has pasted what he got in the mail. Okay.
Because I added the calendar, I think.
You added from a Discourse or what? Like
I forgot. Somewhere I added.
Yeah, because I got
think
from the
I
mail
added from the course
page.
Okay.
portal, yeah. Course
Karthikeyan,
portal, I think.
there are two calendars as of now. So if you added the one from the course portal, that one is most probably the incorrect link. So
Yeah,
if you
the course.
refer to the mail that you received from the official ID, just go to that one and there you'll have the correct link.
Okay.
And I just joined the session. Can someone please post that timings message once again, and if possible, pin it, please?
I will pin his message for now. I will just share it. Okay, I'm not able to pin it. Yes, so now, Shaktivel, do you have any query?
Actually, in yesterday's session, orientation or project orientation session, they mentioned like we will have projects TA session at the same time. So, are we are going to discuss both the things, or it will be scheduled separately?
No, project TS will be different. Okay, we won't be handling, at least I will not be handling the project at least in this term. Okay, so I will only be taking the sessions regarding the theory course. Okay. They might be taken by some other TAs. Okay.
Sir, I also had a question, another one.
Yeah.
Sir, so I had one question and one request. So my request was if you could just post that timing message once again. Actually, I just joined, so I am not able
Yeah.
to see that.
Okay, the timing was 1 minute.
Okay, sir, got it.
Got
Got it. So someone
Yeah.
else. Yes, sir. And sir, my question was that regarding this course. So, sir, as far as I understand, since this is the first term, so there is no set pattern for the question papers or for anything else.
Yeah, till now we have not received any information how the question paper will look like, what type of question it will contain.
Exactly, sir. Sir, so my question was if at all, if this happens, if you'll be borrowing questions from the papers of the degree level areas that coincide with our course, that overlap
No. The
basically.
level of those questions will be quite different from what we are going to discuss in our course. So,
Okay.
okay. So,
Sir, actually,
just for practice, if you want to refer to, you can refer to those questions for the theoretical part, but the level would be different.
I
in the
did, sir.
model.
Actually, I did refer to those questions just to get an idea, and those were like quite high level as
Yeah,
compared
yeah,
to what's
because
been
that
covered.
is a level 3 course and this course is level 2 course. So that's why there is a difference between the level.
Okay, sir. So we'll be getting new questions basically, right?
Yeah, you will be getting
Okay.
a new question.
Okay, sir. Got it. Got it. Thank you.
Or you can take a look at the GAs. Okay, similar level of question you will get.
Understood, sir. Thank you very much.
Yes, Aviram.
Sir, I removed that calendar and I added this link. Now,
Mhm.
again, it's showing the same 2:30 to 4:30 p.m. This wrong date. Like,
Please check once your calendar time settings. Okay.
yeah, this the same message we have pinned that I also pasted that we get from the mail. So that showing this.
Just no, I'm telling that just go to your calendar setting and check the time zone. Okay, what type of time zone you are using?
Okay,
Because
my Indian
I've
time
also
is.
I've also added the same calendar link and for me it is showing correctly. So the link should be correct.
Oh,
For
yeah, yeah.
Friday, for Friday, Saturday, what is it? 9 to 10?
For Friday, Saturday, Friday, do we have session on Friday?
Friday, Saturday, there is a session by
Okay,
instructor.
instructor session are there, I think.
Yeah, you said you have added, right? Because for me, it's showing 8 to 9.
God, is my
Uh,
timing are wrong.
okay, yeah. So for instructor session, I think one is
Yes, Friday, Saturday, it's showing 8 p.m.
Yeah, 8 to 9. That's what I was trying
Yes,
to
8 to
say.
9. Yes.
Yes. Okay, so
yeah.
that is right, means okay.
Mm.
So,
Okay.
excuse me, sir.
Yeah, yes, Ronak.
So, in graded assignment, question related to Hoover laws, but not don't know how to Hoover laws. So, explain
Sorry,
little bit, sir.
question related to
Hoover laws,
okay,
HUBER.
Hubel loss. Okay. Yeah, it is okay. I will explain it here. Okay, now Hubel loss actually it's in
Sir, one
one of
thing,
the lecture. Yeah.
sir, Friday the session is on from the 8, but the Saturday it is from in the afternoon.
Yes, it's different because it will be taken by different
Yeah,
instructor and
someone
probably
said
he
both
might be
the
free on that
days
time.
have the session from 8.
Sorry.
No, someone said both the days the session is from
No,
8.
both the days it's different.
Yeah, then it's okay. Yeah, I'm sorry.
Sir, and one more thing, sir. In the initial days of the session, Levin sir had shared a G Drive link with us, which is now also available in the supplementary content section. The name of the folder was week 1 and 2. But sir, I had inquired with the other TI. I'm not able to remember. I can't recall his name right now.
Puneet, I
Yes,
think.
sir. It was Puneet, sir. So, sir, I had a word with him, and he said that the PPT or the slides PDF that is available, that is for week 1 only. But, sir,
No. It is like a combined PDF for both the weeks. The
okay,
slides contain the content for week 2 also, and the
okay, sir.
collab also. Some of the collabs are from week 1. Some of the collabs are from week 2. As you can see, some collab are named customer churn and the session MNIST, right? Those are used in week 2.
Yes, sir. No, that is clear, sir. My question was just regarding the PDF. It's a combined PDF, right, for week
Yeah,
one and
it's
two
a
both.
combined PDF.
Okay, sir. Got it. Thank you.
Okay. Yeah. Any more query? Yeah.
No, sir, enough time lost.
No. It's okay because this is the first time we are rolling out this course, so it's okay for you guys to have this query. Yeah, this will also help us structure the course better. Okay, so let's do a recap of whatever was covered in the week 1. So week 1, we basically first introduced the need of going from our traditional ML methods to the deep learning models. So can anybody give me the reasons why we need to switch here? Yes, the recording will be made available.
Sir, there are multiple reasons. Like
Yeah,
we have got the first problem is that feature engineering tunnel. So, sir, the manual feature engineering has to be done for machine learning,
very
and
good.
that requires, first of all, that requires domain expertise, and secondly, it's not always guaranteed to be the optimal features.
Very good.
And next, sir, we've also got the problem of the learning patterns. So ML can only learn, at best, it can learn some surface level patterns. but DL allows the model to learn more hierarchical patterns. And sir, the third would be that DL can handle very large and complex data as compared to ML.
Very good. An ability to handle high dimensional data. Okay, so those are basically the issue about our traditional ML models. In those, we have to manually do the feature engineering. There's a limited way in which they can represent any functions. Okay, they do not have a deep capability to represent the nonlinear functions, and of course, to handle the high dimensional data like the images, sequences, okay, text, they are enabled for that purpose. Of course, you can use that, like you can flatten an image and use the traditional ML models, but they will not be able to learn very good representation of that, or they will not be able to attain a very good score on those. Okay. So that's the need that we have to switch from ML to deep learning models. And the first model in the deep learning era that was discussed was the Mcculloch neuron. Now can anybody tell me what is it about? Yes, Shubham.
Like, so the basic term is the model or architecture. What should we call?
The architecture is about the design. Okay. If you will learn about the transformers model later, so let's suppose if I take this as an example. Okay. The architecture, if I am going to say for this neural network, it has basically 1, 2, 3, 4 layers. Okay, in which one is the input layer, one is output layer. There would be 2 hidden layers and the number of neurons in the hidden layer. Okay, so that is about the architecture. Okay, model is the function that we define from what space to what space it is going. Okay. Yeah. So the first model that we have was the MP neuron model. That is the Mcculloch neuron. So can anybody tell me what does it do?
So
Sir, it
basic
takes
neuron.
multiple and there are no weights updates. Threshold, it will assign 1 or 2, 1 or 0 output.
Yeah. So basically,
it works on binary inputs.
Very good. So first of all, what kind of input it can take?
It takes only Boolean input.
Binary.
Yeah, binary, basically Boolean input. Okay, only Boolean input, and what type of output you will get?
Boolean itself.
Boolean output you will get. Okay, so input is also Boolean, output is also Boolean. Okay, now can MP neuron, okay, first of all, let me define how it works. So it's a function from, I should write 0, 1. In some d-dimensional, we will either be having zeros or 1, and it will also map it to either 0 or 1. Okay, so that's the function in which we will define it. And it is basically defined as the summation of xi's. Okay, I belonging to this space. So it's basically nothing but you will sum all your features values. Okay, and you will decide whether this sum is greater than some threshold value. If it is greater than some threshold value, then you will output as 1. Otherwise, you will output it as 0. Okay. So one of the cons that it has, that it does not give the feature importance, as you are just treating all the features equally, because you can treat that this summation is like treating all the feature with weight equal to 1. Okay. Now let's discuss the pros and cons for this model. What type of function it can represent? Sorry.
Gates.
Gates, yeah, logical gates. So any type of gates or any specific type?
And gate or gate, but not XOR.
Not gate.
Yeah. And or, so basically the linear separable function, right? Any linearly separable Boolean function can be represented using MP neuron. Sorry, I should not say any. some of the linearly separable Boolean function can be represented using MP neuron. Not all linearly separable Boolean function you can represent using MP neuron. Okay. So some linearly separable Boolean function can be represented by MP neuron. Okay. So let me give an example, which is a linearly separable function, but you cannot represent it using the MP neuron. So suppose you have a two data points of this class here. Okay, and these are your 0, 0, 1, 0, 0, 1, 1, 1. So green data points are 1 is here, 1 is here. Okay, now this type of data points are linearly separable, right? We can use the line here. Okay, but you cannot represent this Boolean function using MP neuron. Okay, as per the equation that they have given for the MP neuron, that is the summation of the feature. If it is greater than some threshold value, then you will output it as 1, otherwise 0. Okay.
So what's MP neuron?
The McCulloch-Pitts neuron.
May?
McCulloch-Pitts.
Okay,
Yeah.
fine. So how much has been covered, because I joined little late?
We are just starting. Okay, not much yet. Just we are recapping what was the things that were covered in the week 1. Okay.
Okay.
So currently we are discussing that MP neuron can only represent some of the linearly separable Boolean function. First of all,
Sir,
it can
this
only
MP neuron, where was it taught in week 1?
It is one of the 21 lectures. I don't remember exactly which lecture, but one of the 21
week
lectures.
1 or week 2?
Week 1.
Yeah. 1.1. Okay, fine.
Okay. So MP neuron can only represent Boolean function, and in those also only some of the linearly separable Boolean function. So this is one of the example, which is a linearly separable Boolean function, but you cannot represent it using the MP neuron function. Okay. So let's move forward. Anybody has any doubt so far?
So we cannot.
Yeah.
Yeah, but why we cannot represent this one?
Okay, tell me how you will use it. Can you tell me the threshold value?
If we
By
put the threshold
representation,
at
you
1,
mean that, okay, if you put the threshold value as 1, one of these 2 points will get misclassified. By representation, I mean that it should perfectly get a full 100% accuracy. All the points should be correctly classified. For this type of function, we have basically a feature which will have x1 and x2 value. Okay. As per the MP neuron rule, x1 plus x2 should be greater than or equal to. Okay. You can put some threshold value, let's say theta. If it is greater than or equal to theta, then we will set it as 1. Okay. Else we will output it as 0. That's the equation for the MP neuron function. Now, given this set of data points, that 0, 1 and 0, 0 is red, 1, 1 and 1, 0 is green. It is a linearly separable function. I can simply draw a line here. But can you tell me the value of theta for which it is linearly separable? If you put it as 1, then one of these 2 points will get misclassified based on how you choose whether the strict inequality or equality here.
okay.
Yeah. Anybody has any more doubt here?
Sir, is there any inbuilt algorithm in sklearn? I mean, for perceptron, we do have in sklearn, but do we have anything similar for MP neuron?
I don't think so, because it is not getting used anywhere. It was a very simple network that we started with. Okay, so I don't think so it is getting used anywhere. It has a very limitation power, because it can only use for Boolean function, and that also very few linearly separable Boolean function it can represent, not all. Main keyword here is it cannot represent all linearly separable Boolean function, only some.
So for this problem, the theta should be more than 1. If it is more
If
than
you use more than 1, then again this point will not get classified correctly, because the line will go somewhere like this.
yes.
Okay, so one of these 2 points will get surely misclassified here. Okay. So always just remember this. If we are saying that it is represented by MP neuron here, so by that we mean that it should get 100% accuracy. All the points should get correctly classified. Okay. Only then we say that it is getting represented by this MP neuron model. Sorry, just give me 1 minute. Yeah. Any more doubts here?
Sir, if it is x2 minus x1, then x1 minus x2.
See, it's not, because the definition of MP neuron is you will take the summation of all the features. Okay, all the weights are assigned basically 1. Okay, so it's just a summation of the features. You cannot use -1 or something here. Okay.
Okay.
Yeah, that's why this equation has to be just x1 plus x2 only, where x1 and x2 here are basically the features. Okay, or if you want for the confusion, you can take it as like f1, f2, feature 1, feature 2. Should we move ahead?
So just to clarify, so does it have any associated weight or not?
No. It does not give any importance to any feature. It treats all the features equally. So that's why I said it's like it is not giving any importance to the feature.
So sir, does that mean the weights can be equal as well, or there are no weights assigned?
There are no weights. Okay. And if you want to call them weights, then just all the weights are equal to 1.
Okay, sir. Thank you.
Let's move ahead. So the next model that comes out was the perceptron. Okay, we all have studied perceptron in MLT. So,
Sir, so how will a AND model be represented if it is an OR?
and it can easily represent, because in the AND this point will also be red, right? So and you can use like greater than equal to 2 threshold. Okay.
Okay, sir. Okay.
And in the case of
So
OR, you can use a line like this, greater than equal to 1.
So what's this kind of model?
Model is the MP neuron here.
No,
And if you are
this
taking a Boolean function, you are asking.
This kind of red and green.
So this is some Boolean function.
Okay, some random Boolean function.
Yeah. For which if the input are like this, you will output red. If the inputs are like this, it is a green, means 1. Okay.
And XOR, sir, how will XOR be represented?
XOR also it cannot represent because it is not linearly separable. Okay. It can only represent linearly separable function, and in that also it cannot represent all. Okay. It cannot represent all linearly separable. Only some of the linearly separable function can be represented. Okay.
Yes, right.
Should we move forward?
Yes.
So let's move on to the perceptron. So I will go a little bit fast on this part because we have already seen this in MLT. And I hope all of you have done the MLT. So tell me, what do you know about the perceptron algorithm?
Reduces the time.
So adds the weights to the.
Yeah, we will add the weight. Okay. So what about
Learning
the input?
rate as well.
What about
You can use non-binary inputs also.
very good. What about the output? Output is still binary.
Yes, sir.
Yeah, binary output only.
Yeah, we have introduced the features. Now, what type of function it can represent?
So linear only.
Again, linearly
Linearly separable.
separable.
Yeah,
Yeah,
linearly
it
separable.
can
Yes.
represent if we have any linearly separable function with some margin. Okay, again, perceptron has this margin thing. Remember from the MLT. Okay, if only the yes, okay, any linearly separable function with some positive margin can be represented by perceptron. Yes, whoever has doubt.
So like the one you have told, like it will only do the linearly separable model. Like if we give a nonlinear one, then what will be the output of this model? It will not evaluate, or it will give
For
some
the perceptron,
yeah, perceptron.
yeah. So in the case of perceptron, if you see the implementation that is done in the scikit-learn, have you done the MLP?
Yes, sir.
Okay, if you have done the MLP, then that is good. Remember, there's this one parameter in the scikit-learn API that is the max iter. Okay,
Yeah, max
so it will
iterations.
run till the max iter. Okay, let me first write down how the perceptron algorithm works. Okay, then after that I will tell. Okay, so perceptron algorithm is basically will start with a random weight vector. Okay, and we will do this following. That is, do the following for a fixed cycle. By fixed cycle, I mean that if my data points are like x1, x2, x3, xn, okay, the order in which you are going to cycle through the data points will matter in the case of perceptron. If I'm going like first x1, then x2, then x3 till the end, then this can give a different result than if I go like from xn, then xn minus 1, like that. Okay, so in a fixed order of cycle, you are going to train your model. Okay, so in a fixed cycle, you will evaluate the performance of the model, that is using the weight vector times your data point. Okay, now if this correctly classify, okay, this will give the y hat. If y hat is equal to y, then you are not going to do anything. Okay, but if it is a mistake, then you are going to update your weight vector using this rule. Okay,
Previous weight vector.
yeah. So I can write it as this wt plus 1 equal to wt plus x, that is your data point for which it has made the mistake. Y is the label, the true label for the data point for which it has made the mistake. Okay, and you are going to cycle through the data points in that order. So suppose you are starting from x1. Okay, x1 is correctly classified with the current weight vector, x2 is also correctly classified, but on x3, let's suppose it has made the mistake. Okay, then you are going to update it using the x3 and its corresponding true label. Then you will again start from the x4, that is the next data point, and again cycle through it. You are going to keep doing it until it converges. By the convergence criteria is decided when one full cycle is completed without any update in the weight vector. Okay. Now, in the case of the scikit-learn API that it is used, if you are going to set a max iter value there, okay, what does it do? That it is going to do this entire computation by the max iter times. If by that time it got converged, then okay. Otherwise, whatever the last weight vector value you will get at that number of iteration, it will output that weight vector. Okay.
So, but the answer, like the since it is not the linear separable data, the value would be wrong also.
Yes, yes, yes. In that case, it will be wrong.
Okay, fine.
So it must converge as per our requirements like this, no? The value we set, like tolerance, whatever we setting. If it's
Yes.
not converging, then we apply this else part like this.
Not the tolerance one. Here, what it just check the whether it is getting correctly classified or not. So we'll check the W transpose Xi value. You generally
Mhm.
put that if it is greater than equal to 0, then you will output it as 1, otherwise you will output it as 0. Okay.
So is it not related to converging or anything like?
Converging is only related to the whether it is able to correctly classify all the data points or not. When it is able to correctly classify all the data points, we say that perceptron algorithm converged.
Okay, sir.
Otherwise, it will run till the max iter value that you will provide in the scikit-learn API. Or
Yeah.
else, I think there's this tolerance parameter which denotes the loss, how much loss it is able to reduce.
Okay.
Okay. Any more doubts? Okay. So after perceptron, let's so we can also see perceptron with the non-linearity introduced using the sigmoid function. Okay. So what we do is we have this x. Okay. We will multiply it with some weight vector. Okay. The output of the weight and the data point multiplied, we will feed that output into the sigmoid function value. Okay. And this we can treat it as a probability because the output of the sigmoid function lies between 0 and 1, right? So that can be treated as the probability, and based on the threshold value for this probability, we can decide whether the label is 1 or the 0. Okay. So instead of the hard step function that we had in the perceptron, because the perceptron rule was this, it was a kind of a step function. Either it is 0 or it is 1. Okay. So first of all, it was not differentiable because of this step function. Okay. So we introduced this smooth non-linear function to capture the non-linearity part. Okay. And also to introduce the notion of probability, which can help us adjust the threshold value based on our problem that we are working on. So for example, for some of the problem, you might want to lower the threshold value, that you are okay if some of the data points are misclassified. So if I take an example, it can be like you are training a model for the airport security check, and you do not want that any objectionable object get past the security check. So you are okay if some of the non-objectionable object are getting misclassified, but you do not want any harmful object to be get passed through the security check easily. Okay. So in that case, you can lower the threshold value, and in some other case, you can higher the threshold value based on your problem. Okay. So yeah, this basically the model is for the logistic regression. Yes, Shubham.
So like my question was the first, that how does the probability brings into non-linearity?
So the non-linearity is basically because of its non-linear function that we are applying on this uh, input of W transpose X, that was a linear operation. On this, we are doing a non-linear operation. Okay. So the non-linearity is coming from here. We say it as a probability because the output of the sigmoid function lies between 0 and 1, and probability also lies between 0 and 1. Okay. So the output of the sigmoid function, we treat it as a probability. Like what is the probability for my data point belonging to a class 1? Okay.
So basically, the sigmoid function is the like 1 divided by 1 plus e to the power minus x, right?
Yes, yes. The
So
sigmoid,
like for example, like every time, how will means based on that function, any point will lie, like it will separate any point based on that.
no, it won't going to separate any function. Again, it's just that sigmoid function also not able to separate a non-linear classifier. Okay, so you have a non-linearly separable data set. In that case, also it's not like it is going to give you a non-linear boundary. Okay, just for one sigmoid, you will not be able to get it. Okay, of course, you have to stack multiple such that in that case, you will be able to do it. That is the case of neural network that we are going to see later.
So sigmoid function is for activation function, if I'm not wrong. Like I've just little bit
Yes.
forgot.
Yeah, activation function. It is one of the activation function, and it is the basically starter of the activation function that we started with.
Represented by z, that e to the power minus z, so that z has like that.
Z is basically the input that you are feeding to the sigmoid function here. Here we are going to feed the W transpose X value that you are going to get.
Got it, sir. Thank you, sir.
Okay.
So After it converges, the accuracy will be 100%. Like
it is not necessary. With just this simple model, it is not necessary. Okay.
Accuracy can never be 100% for any model, I guess.
For the training data, it can.
Yeah, but test real life data is not possible.
Yes, yes. In that case, no.
yes, sir. I mean for training data only.
For the training data also, it is not necessary that a simple network like this can do the 100% accuracy. There's this universal approximation theorem that Sir has told that was for one hidden layer representation also you have to include. Okay, that we will see it later. That universal approximation theorem tells us that with one hidden layer of complexity if you include, then you will be able to achieve almost 100% accuracy on the training data at least. That we'll see
So
it
if we
later.
include one hidden layer, then we are almost sure for all types of data, it's 100%
Yeah, it can
accuracy.
almost approximate. Yeah.
Okay, fine.
We'll see it later. For now, is it clear? The logistic regression part?
Yes, please move ahead, sir.
Yeah. So now the idea is simple that here we were just having one input neuron, one output neuron. Okay. So we'll just extend this idea. Okay. And we will introduce a architecture of the neural network. Okay. So a general architecture of the neural network will look like we will be having a input layer. We will be having some hidden layers in between and an output layer. I think all of you are a little bit familiar with this architecture as it was already seen in the MLTV12. Okay. So input layer is the number of neurons is same as the number of features you have in your data point. Output layer number of neurons depends upon your problem, whether you are going with the regression or classification. In the classification where you are doing the binary classification or multi-class classification. Okay. If you talk about the hidden layer, how many hidden layers should be there? How many number of neurons should be there in the hidden layer? These all the things are the hyperparameter. You have to tune it based on your use cases. Okay. Generally, the number of neurons in the hidden layer are we draw with the power of 2, like 128, 256. Okay, that's the general that we follow. But again, these all things are heuristic. There's no proof of that. Okay, and these are all the hyperparameter that you have to tune it for your model that you are building. Okay. Now, as moving.
Sir,
Yes.
sir, I have one question. Sir,
Yeah.
other than layers, by layers, I'm including all input, hidden, and output. Other than layers and activation function, is there any other term for neural network that we should be aware of?
There are technically many terms that will come, like the optimizer that you are using and the regularization that you are using. But so far we have not covered those. So until that
Because
comes, I
slowly
think
you are going to introduce those, right? And as we move
yeah,
with our
like in the lectures, I think Prof has used 2-3 terminologies like Adam and the dropout. Okay, Adam will take time if you want me to cover, but dropout, if you want, I can do a little bit touch upon the dropout because that is simple. Okay, now before moving forward, let me also introduce you one term that we were talking about, the universal approximation theorem. Okay, in that theorem, what it tells that a model architecture in which we have only the input layer, one hidden layer, okay, and the output layer. And with this, it is able to achieve or approximate any function. It can approximate any function. We do not talk about the case of generalization here. We only talk about the case of with respect to the training data. That is, on the training data, it is able to approximate it very well with just one hidden layer. That's the universal approximation theorem. We are not going to discuss the proof of that. You might gain more knowledge about this in the DEL course that is there in the degree level. In that course also, we do not discuss the proof. We just discuss the visualization of that. So it's just a theorem that you can just remember that a universal approximation theorem state that with one hidden layer, you can approximate any function, but we do not talk about here the case of generalization, that how well it will be able to generalize. Of course, it is not going to generalize it well if you are able to approximate the training data itself fully. And another thing that it does not tell is the number of neurons that are there. It does not tell how many neurons should be there in those hidden layers and all. Okay, it's just that there exists some amount of neurons and you have to do some amount of training and all, and with that you will be able to approximate it well. Okay, now let's talk about
Approximation means what we are trying to.
approximation means
Yeah.
you can say that it is able to classify all the data points correctly. Okay, so
The test data we'll be
Why
getting
we
like
say approximation then?
we say approximation then because there might be like a little bit error. So
Okay.
some
To
point amount of,
an acceptable level. Okay.
yeah, just very low error.
Maybe 70% or
Not more than that you can approximate.
okay, 95%, whatever.
Yeah.
It is. Okay.
And in the test data, we can expect 80 to 85% or something.
No. Test data you can surely expect below than that, because if you are going with such high good amount of result in the training data, then it's more likely to overfit.
Okay. So
that's why we say
60%.
that like there's no threshold like how much it can. Okay,
Okay,
that's why
it
it
can
says
go
that
in.
it cannot guarantee about the generalization part in the universal approximate theorem. It can
So
only
it
talk
can
about
go
that.
more and it can go less also.
It can get less. More likely it can get less because it's
Okay,
likely to
more likely
overfit.
to be less.
Yeah. But there's
Yes.
no threshold like it should be around 60, 50. There's no such talk about that. It's just that the informal definition is this, that with just one hidden layer, you can approximate any function, okay, with a sufficient number of neurons in the hidden layer. But it does not say how many neurons should be there. It does not say how much or how good it will generalize it on the test data or unseen data. All those things it does not tell. It's just that you can approximate the training data.
Why it is important for us to understand this universal?
It is important for you to understand for the capability of neural network. Okay, that these deep neural network are, if you are able to do this in one layer, then with multiple layers and with some good amount of training and the good amount of data, you will be able to generalize it also. So our neural network are capable of learning the data and handle it appropriately. Okay, so that's why it's important.
Thank you.
Yeah, so basically from now on the week 2 part will start. There's a universal approximation is also part of it.
Sir,
yes.
So like as we know that the old GPT models works on the BUT model, BUT architecture. So how does it look like? Like it looks like this only, or it looks like more complex?
Which one?
Like the architecture, BUT architecture, BUT architecture.
BUK. Oh, okay, BERT. Okay, BERT.
Yeah.
Okay, those are very complex. The transformations, the transformer models, those will come.
Like the transformer is a model or a architecture?
Transformers are architecture. Okay. The model name is transformers. Okay. You will see the architecture. Architecture is basically about the design of the model. Okay.
Yeah.
So how the input will be getting handled. Okay. So how many layers should be there. So those we call it as
architecture. Is a model.
Yeah, transformer is a model. Yeah.
Okay.
So transformer is a very different model from these simple neural network that we have. Okay. So many things will come in between the encoder, decoder, multi-head attentions, and many things will come. Okay. So that you will see, I think, around week 11 or week 12. So wait for that. Yeah. So, okay. Any more doubt here? Okay. So let's talk about the classification and regression case that we represent here. So if it's a simple regression problem, okay, then in the output neuron, we will only be having one neuron. Okay. And in that, we will be only using the linear activation function. That is, whatever the output will come, we will just directly use that output without applying any further activation on that. Okay. If it is a binary classification problem, then also we only use one output neuron. and in that we will be simply applying the sigmoid activation. And based on the threshold value of the sigmoid activation, you will output it as 1 or 0. If it is a multi-class classification problem, then we will represent our model as like this, that the output will be a vector, okay, between it's of a dimension C. C here represents the number of classes, and it will be a binary vector. Okay. So if let's suppose we have a 5-class classification problem, then it can output like this. Okay, where this 1 represents that the true class is the second class. Okay. So in the output neuron, the number of neurons would be same as the number of classes that you have. And in that case, the activation function that you are going to apply will be the softmax activation function. Okay, so softmax activation function, if I talk, it's basically e power ai divided by the summation I e power ai. Should use j here. Okay, so basically you are going to get some linear combination values in the output function. Okay, so you might get something like 25, 42, 31, 2. Okay, then you are going to turn this into probability. Yes, Saurabh?
Sir, are these activation function hyperparameter or these are fixed?
For the output, these are the general cases that you are going to use. That's why we are discussing. For the hidden layers, okay, generally you start with the ReLU activation, then maybe you can switch to GALU or something else, depending upon how would it achieve the result. Okay, for the output case, these are generally fixed. Okay, if it is a regression, then you are just going to use the linear, because only the linear activation function can lie between any real values. Okay, if it is a binary classification, then you can use sigmoid. Okay, or else if it is a multi-class classification, use softmax.
Okay,
and that's why we are discussing it now. Okay. Yes, Shubham.
So here in multi-class classification, we can also use sigmoid and take the probability that has maximum.
But that will be not be see, in the sigmoid it will be like an independent case. Okay, because how the softmax activation function will work, it will give you a probability distribution. That means it will transform. Let's suppose you got this vector, you have 4 classes, and that's why you have 4 neurons in the output layer. Okay, so after doing the linear transformation, you got this, then you are going to turn this into a probability distribution thing. That means the output vector that you are going to get would, after applying the softmax, might look like something this 0.3, 0.1. Okay, so what will happen? All of these will sum up to 1. Okay, and with that, whichever has the highest probability, you are going to use that. In the case of sigmoid, it's like an independent thing because it will not sum up to 1.
Yeah, but
yes.
we can use na.
See, if you want to use, you can use, but it's not good for you to use sigmoid. Softmax will be a better choice because it will give you a probability distribution across all the events. So among all the classes, which one has the highest probability? In the case of sigmoid, you are assuming that each one has the independent version of it.
Basically, this is logistic, so that's why we are using probability or something like that. The whichever is highest.
Yes,
and so also because sigmoid, if we keep using, that might work, but it will slow down the convergence. It will cost us a lot of time, which softmax helps us in overcoming.
Yeah, softmax is basically a generalization of the sigmoid function only for the case of multi-classification.
So we can also use the parameterized ReLU for quick convergence.
That you can use for the hidden layers.
Hidden layers. For output layers, we have to use softmax.
Yeah, for the output layers, the activation functions depends upon your problem. Whether you are going with the regression, binary classification, multi-class classification. Okay.
Like so softmax is only for classification.
Multi-class classification. You can use it for binary classification also, but for the binary case, it's sigmoid. Softmax is basically a generalization of the sigmoid function for multi-class classification. Okay, just like we have a logistic regression for the binary classification, we have softmax regression The only change between logistic regression and the softmax regression is we use softmax activation function instead of the logistic. It's just a generalization of that. Okay. Any more doubts? Okay. Now about the activation. Yes. Okay. If no doubt, first, let's see, okay. Do anybody has any doubt? First, let's see how you are going to represent your weights and the bias. Okay, especially in the form of vector in the matrix. Okay. So first of all, can you tell me what will be the size of the matrix that you are going to use here? If anybody has seen the lecture. From this layer to this layer, what will be the size of the matrix, wet matrix especially, that you are going to use? Because what we are trying to do here is, if you want, we could have done it with this by taking each vectors here. But in that case, we have to do a loop here. Okay, and looping will make it more complicated and slow down the process. So we do the vectorized multiplication here. For that,
Yes,
introduce this
3 cross 1 into
So is it 3 cross 2?
3
cross 2.
3 cross 2 and 1 cross 3 cross 2 for weight and 1 for bias 1 cross.
So 3 cross 2 it will come.
No, it will be 2 cross 3 actually.
Whatever.
No, it depends. Okay. So the weight matrix with the general notification, it will be 2 cross 3. Okay. For the bias, it is correct that it will be a 2 cross 1 vector. Okay. So in general, how it represents is basically the number of neurons in the next layer times the number of neurons in the previous layer. Okay. So this is how the weights are going to stack. Okay. So in the first row, okay, all the weights that are going to the first neuron from the previous layer. Okay. So this weight, and this weight. Okay. These are going to stack as the first row in your weight matrix. Similarly, the second row represents the weights that are going to the second neuron from the previous layer. Okay. Biases are simple, that B1 for this and B2 for this. Okay. So that's how you represent your weight and bias matrix and vector. Okay. Is the structure clear? Yes, I will share it.
Yes, sir.
Okay.
So,
this is
before you have told that it will be 2 cross 3. You are telling about that weight matrix.
Yes. Weight matrix 2 cross 3. 2 rows, 3 columns. Okay. So number of neurons in the next layer times number of neurons in the previous layer. That's how you are going to represent the weight matrix between 2 layers. If I go about this big example here, tell me what will be the weight matrix size between these 2 layers?
5 cross 4.
6 cross 5.
6 cross 5.
6 cross 5. What about these 2 layers?
3 cross 6.
3 cross
3
6.
cross 6.
3 cross 6. Okay. And what about this?
1 cross 3.
1 cross 3.
1 cross 3. Okay. What about bias in this layer?
6.
6 biases.
6v1.
3,1.
Very good. Okay. Yeah. So what's next is number of parameters. So we have all solved these type of questions in the MLT. So tell me, for this neural network, how many weights will be there between these 2 layers? You can count it. 1, 2, 3, 4, 5, 6, 7, 8, 9 is there. 2, 3,
9
5.
cross 5.
45.
45.
45 here. And how much is here in this? 36 is there.
36.
Okay.
81.
Weight is 81. What about bias?
13 bias.
13 biases.
13 bias. Okay. Important note: we do not have bias in the input layer. Okay. Except input layer, all layer will have bias. So the
So,
total
but the
parameter.
end is the output layer. The end part is the output layer. So how is it
Uh,
bias?
It will also have the bias. We're going to do the add the bias here also. Okay.
Bias should be there everywhere. It can be 0 at times.
Yeah, it can be 0, but we do not have any bias in the input layer. That's what I'm. That we do not. If you're counting for the number of bias, we do not count this 5 here. Okay.
Sir, how weights 81? I'm not able to understand.
See, between these two layers, there are 9 neurons in this layer, 5 neurons in this layer.
Yeah.
So the weight matrix size it will have is 9 cross 5.
Huh.
Okay. So basically there are 45 weights because each neuron here
Got
will
it.
get connected to each of them. Similarly, there will be 36 weights in this. Okay. So
Huh.
45 plus 36 is 81.
Got it. The whole matrix size you are saying, right? If we
Yeah,
count
you are going to
rows and
basically
columns.
count these
Got
number
it.
of element in this matrix. Okay. Similarly, if I talk about the bias, it's 9 plus 4, 13.
Bias is for output, na? For the first
For
one, the output is
hidden
second.
also, it just you do not count the input
Yeah,
layer.
yeah. Even in the hidden, the first one will be the input and the second one will be the output. Then the second output will become input and the third one will become output. So we have
Yes.
two outputs if you see, like, you know.
Yeah,
That's
kind of you can say.
Yeah. Thank you, sir.
So the total number of parameters is just a summation of these two, so 94. Okay. So it is always important to see how many parameters are there, because if the more parameters are there, the more complex your model will become. So according to that, your data should also be there. Otherwise, it will overfit. Yes, Shubham.
So like you have told about the number of parameters. Like when we see in the GPT models and something, they told that there are 1 billion parameters. These are the
Yeah.
parameters. Okay.
Yes, see those, because in that there are very complex things that are going on. Here we just have a simple weight matrix between two layers. I cannot use the terminology because we will not be able to understand. Do you have any idea about the transformer models?
No, sir, nothing.
In those, basically, we will be for like in one layer we will be having multiple heads. Okay, so it's like we have one layer in which multiple things will be there, and in each those thing where there we will be having like something 3 matrix will be there, and then we will stack such of these layers multiple times, so the parameters quickly explodes. Okay, so that's why they have like billions of parameters in that case. Okay, in the neural network it's not going to blow up so easily, but there it can blow up easily. Okay, and apart from that, not just in that transformer model, before that also you have to do the embedding. By embedding we means like if you are going with the, let's say, sentiment analysis, then you will be having the text, you have to convert it into some vector form, you have to tokenize it. For that also we need parameters. Then comes something called as the positional encoding, because the position of a text depends upon the use case. So I am going home. Okay, the position of I am going home, these depend. So you have to do the encoding of these things also. Okay, so
So
all
like,
of these.
like the feature engineering in what we do in MLP.
No, that is different. And this is different. Okay, these are all learned here. Okay, in that we do it from our domain knowledge and things, but here all these encodings are getting learned. Okay, along with the model. So that's why the number of parameters quickly increase in those models. Okay, and only then they are capable of learnings and doing various these tasks related to like summarization, interaction, chatbots, and all, because they are very complex models. We'll see them when the time comes. Okay.
So like anyone can create them. Like if we are like students at level, like can we make a simple
You can do a simple simulation, okay, for like, but it's going to take some amount of time to train those model and then fine tune it. But of course, you can do it. Not, of course, on that level, but for a small, simple model, you can create. Okay.
So can we take DeepSeek and these models as a base model and then fine tune for our use case after doing
Yeah,
this course? I mean,
after doing this course, I'm not sure because the
course,
content.
like, I mean, entire course as generative.
Yeah, of course. Because in the later course, like in the DLP and the LLM, you will be, of course, learning how you do the fine tuning and those in much more detail.
Sir, I'm waiting for the course where I can finally be able to create like fine tune the model. Like,
See, that is, I think, a part of project. In the project, we are doing the fine tuning. So in
but
the course, I think in
without
the
the
course it
course,
will come later. That part will come in the later in the course at least.
okay, sir.
Yeah. So let's move ahead. So let's see how the multiplication will happen. Okay. So this is your input layer. Okay. You have 3 neurons in the input. That is your data points lies in R3. Then suppose this is your first hidden layer. You have only 2 neurons. Okay. Now I hope I have taken the right notation as per the lecture. Sir is used the pre-activation stage as the Z and the after activation is A. Okay. So first of all, what will be the matrix size here?
2 cross 3.
2 cross 3. Very good. And the bias would be 2 cross 1.
2 cross 1.
2 cross 1.
So how the multiplication will look like? Your weight matrix multiplied with the X plus B. That will give you Z. Okay. Z is the pre-activation stage. That is, you have not applied the activation part here. It is just the linear transformation that you are doing. Now let's see whether the matrix multiplication is consistent or whether it is giving any error or not. So our weight matrix was of size 2 cross 3. Our input X is of size 3 cross 1.
2 cross 1.
It will give us as output 2 cross 1.
2 cross 1, yes.
Bias is also 2 cross 1. Final output is a 2 cross 1. Okay, which is the size of, yes. Yes, Pranshu.
Sir, it doesn't have hidden layers. I mean, we have that input layer and then output layer.
This is not the output layer. This is just one part of the neural network that I am using currently to explain this vectorized multiplication.
Okay, as a separate, okay, sir.
Yeah. Okay.
So
later part we'll
we
see
can
it.
conclude that WX and B must have same dimension no matter what, right?
Yeah, of course. Only then the addition can happen.
Yeah.
Right?
Yeah.
Okay. This is just one part of the neural network that I have cut down and I'm using it for the explanation. Otherwise, the same thing is happening in this big network also. Okay. Now, this Z here represents the pre-activation space. Okay. Later, we will apply it any activation function that you are using. Suppose if I am going to use the sigmoid, okay, I'm going to apply it on the element wise. Element wise by means because the Z here lies in 2 cross 1. Okay, so it will have one element here, one element here. Okay, so we're going to apply sigmoid on each of these elements. Sigmoid of this, sigmoid of this. Okay, that's what it is mean by element wise operation. Okay, so the activation operation happens element wise. Okay, here the operation happens like your general matrix multiplication and the addition. So this after activation, we call it as A. Okay. So is this part clear? How this multiplication happens throughout the network?
Yes.
Yeah. Now let's move back to this part. Okay. So generally we call the input layer also as the zeroth layer. So that's why I'm calling it as A naught. Okay. Then we will be having Z1, A1, Z2, A2, and then Z3, A3. Okay. So between these two, how it will happen? You will get Z1 as W of order 6 cross 5 times A naught. Okay. A naught is of R5. plus bias, which will be of order 6 here.
6 cross 1.
6 cross 1. Okay, so Z1 you will be getting in R6 cross 1. Then you will apply activation function. So currently let me use any activation function we are using, Z, on the Z1. That will be equal to A1.
Sir, W6 and A05 both dimensions are not matching, so how will they multiply?
It will match. W is of order 6 cross 5.
Oh,
Okay.
it's written 6. Oh, sorry. I thought it's 66.
6. Okay. So after this A1 will be A1 is the output of operation between these two layers. Now this
Excuse me, sir.
Yes, Rona.
Sir, activation function apply on vector or element?
It is applying on the vector, but it is applying element wise. So that means, suppose if you have this vector 25, 42, 31, 2, on each of these elements I will apply my sigmoid function if I am using sigmoid as an activation. Sigmoid of 25, whatever value it will come, that value will come here. Sigmoid of 42, whatever value will come here. So element wise I am applying activation.
Yes, sir, clear.
Now this A1 that I got as an output between these two layers transformation, okay, this output will be taken as an input for the next layer transformation. Okay, that is my Z2 will be this W, which is of order 6
3 cross 6
times A1, which is of order here R6, plus this B here, which is of order R3.
R3.
So I'll get Z2 in R3. Okay. Now after we apply the activation, okay, this will become my A2. Okay, so each of these layer will have two stages. One is the pre-activation stage, one is after activation or post-activation stage. Okay. So Z here representing the pre-activation stage with the, that is before applying the activation. After applying activation, we are calling it as A. Okay.
So I have one question.
Yeah.
So like as you in this diagram, the Z1 is a pre-activation state, and the like A1 between A1 and A2, the pre-activation state is the Z2. So like all these Z1, Z2, Z3 means how are they contributing to the final result?
They are getting applied with the activation stage, okay, in which we will introduce the non-linearity. Okay, so that's how they are contributing.
Like
first
so
you are
like
doing the
Z1
linear
is
transformation.
Yes.
First you are doing the linear transformation here. Okay.
Yes.
That will project your initial data points into some different space. Then you will apply activation function to capture the non-linearity. Then again you will doing the linear transformation. Then again you will apply that non-linearity.
Okay, we are activating that Z1 only. Because I understood this.
Sir, Z2 not able to understand, sir.
Okay.
Yeah,
so,
W3 cross 6. Then after that A1 R6, like what is it?
A1 is coming from here.
Yeah, A1
because,
is input. I know that.
Yeah, A1 is the input that will multiply it from here, right?
But what is 1 R6? Like I'm not.
A1 is this R6. I am writing the size of A1.
Okay, 6 cross 1 is R6.
Yeah. So if you want, I can remove this if it is creating the confusion.
No worries about it.
It is just to mention the size I am writing it. But A1 just I was emphasizing that A1 belongs to R6.
Yeah, that I know.
Okay. So if I'm going to write a general equation, how the forward pass equation will look like. So copy this page. Okay. So again, we have this A0, Z1, A1, A2, Z2, A2, Z3, A3. Okay. For any Zi, the equation is Wi A. What will come in the subscript? AI or something else?
A0.
For any I layer, I minus 1.
I plus.
I minus 1.
Because if you notice, for calculating
Previous
Z1, we are using previous layer output. Okay,
Yes.
A naught. For Z2, we are using A1. Okay, so AI minus 1 plus BI. Okay, so you can write it like this is W1 because it is between the first hidden layer and the input layer. Okay, here you can write the matrix between these two layers as W2. Between these two, you can write it as W3. Here also you can write it as V1, V2, V3. Okay. So any forward pass equation will look like Zi equal to Wi, which is the wet matrix, Ai minus 1 because we are using the output from the previous layer, plus Bi. Okay, that is your vector for the bias.
Okay, sir.
For the activation stage, it is just any activation that you are applying on Zi. Okay, so here the subscript will remain same. Okay, so G here denotes the activation function. It can be sigmoid, ReLU, parametric ReLU, GeLU, CeLU, ELU, anything. Yes.
Sir, how you had taken AI minus 1?
AI minus 1, that's why, because if you look at how the forward pass happens, this is the input. Okay, it will get multiplied with this wet matrix and gives me Z1. Okay, so Z1 is W1 A0 plus B1, right? So
Yeah.
everywhere it is 1 and here it is 1 minus of that. Okay, then we will just apply activation function and we will get A1. Okay, then this A1 will be fed with W2. So it's Z2 is W2 A1 plus B2 and A2 is Z of Z2. Okay, so everywhere it is 1 minus because we are using the output from the previous layer to compute the output for the next layer.
Okay, sir.
Okay. That's why it is 1 minus here in the subscript. So clear for everyone?
Yes, sir.
So the forward pass done, equations done. Now comes the loss function. Okay. Now loss function also technically depends from use case to use case. So somebody asked about the Huber loss in the starting. So let's discuss that also with this. For the regression, that general loss function that you can use is the sum squared error. Okay, that is y hat minus y whole square. You can divide it by 2 also for the mathematical convenience. Okay, and as I said initially, in the case of regression, okay, the output neuron will have only one neuron. Okay, consider that this is the output layer here also. Okay, now there are different choices are also available for the loss function. It's not limited to the sum squared error. Okay, it depends upon your use case and how your data is. So if you want that error to be penalized heavily, then you can use the sum squared error. If in your data set you have like outliers, okay, and you do not want to be get affected by it. Okay, if some outliers are there, then you can simply remove it. But if many out, Ronak, do you have any doubt? But if you have many outliers in your data set, then if you are going to remove it, it can create the condition for the data loss. So in that case, you can either go with the mean absolute error, but in that case, you will not be able to get a differentiable function. So you might not get a optimum value. Okay. There's one more function that Faraz discussed during week 1, that was the Huber loss. So it was kind of a combination of MAE and the squared loss. Okay. So let me write the function. So for the
Sir, in what lecture it is discussed the Huber loss?
In one of the lecture in week 1, I think it was about when Sir discussed
Second
creating
lecture.
custom loss. I think it was in the PyTorch one. In creating custom loss function, he has discussed.
Custom loss functions.
Yeah. So one thing that
Can you repeat the Hubbard loss one combination of
yeah, I'm repeating. First, I just want to say one announcement that please use your IITM student ID next time to join it. Okay. I will not allow it from the next time. Well, some of them here are from using, I think, personal email ID. Please use your student mail ID to join. Okay. Yeah. Now comes for the Huber laws. So it was kind of like a combination of your absolute error and the squared error. Okay. So what you are going to use that there would be some delta quantity. Okay. So delta is basically your absolute prediction. Okay. So can this is like a parameter here. Okay. You can set some parameter, what parameter value you want to set, and based on that, if your loss value is greater than this, okay, so you can then use the linear function, that is your absolute error. Okay. If this delta is less than 0, then you can use the quadratic error. Okay. Linear loss means you can just simply use the absolute value of prediction minus target. Okay. So linear loss, you can define it as this delta times the absolute value of predicted minus the target. Okay. And yeah. And if it is the quadratic loss, then you can just use the half to delta. Okay. Minus was there plus then value of predicted minus target square. Okay. Let's recheck this formula once. Okay. But it was
So
like
isn't it interchanged? I mean, quadratic and linear.
when the residuals are less than the delta, we should use the quadratic, I think. So let me just
The
recheck.
conditions are correct, sir. The conditions are correct that when residues are less, you use quadratic loss. The formula part.
The formula part, yeah. In which one? Quad loss or linear loss? Hello?
So quad loss.
Okay, quad loss. Yeah. Yeah, let me just recheck it then once.
Sorry, is this the same like ridge and lasso?
Yeah, actually, Huber loss is a combination of L1 loss and L2 loss.
Yeah, so I think it should be just a squared one then. Half squared minus target square, and we can multiply it with the delta. I think this should be correct then. Okay. Just recheck this part, but okay.
Yeah, I'm checking it with.
For the Huber loss. If it is this, then half of this, then yeah. So it is less than 0.5 a square, yeah. Okay, so the delta will not come here. If it is greater than 0.5 residual square minus that, okay. At this part it has error, so 0.5 residual, 0.5.
Yes, I will
Delta square.
subtract the quad loss. Yes.
Delta square. Okay, now it's okay. Okay. Yeah, so that this was the Hubel-Loss. That is the combination of both of them. So this is generally good start. Okay, if you have many outliers and your data is not clean very much. Okay.
So I'm checking with a ChatGPT. It's giving something else, like little bit difference, like.
Okay, so in the official Wikipedia page I have opened. Okay, let me share the screen for that. Okay, that is this one. So okay, that is the correct one, I believe. And in the lecture also, I believe the sir is taught in this way. Okay, otherwise we'll follow with whatever the sir is mentioned in the lecture.
So with this
Yeah.
again, it's spread minus target itself. What you have written was correct.
Yeah. Okay. So and then whatever was mentioned in the code for the sir that sir has written, okay, we will follow that. And then if there's some mismatch between any of the source, okay. So I believe this should be the correct. Okay. But let's move forward without the formalized can. Yeah. So let's discuss about the need. We can adjust the formula later on also. Need is that if you do not have much outlier and you want a optimal convergence also, and you want to penalize the error heavily, then you can go with the squared error in the case of regression. Okay. Or else you can go with the Hubel-Loss. That is beneficial when you have outliers and you also want a smoother convergence. Because in the absolute error, you can handle the outlier case, but it may not give the optimal result because it is not differentiable. Okay. While Hubel-Loss is mix of both, so it is good startup loss function in general. Okay. So that was for the regression. For the binary classification, we generally use with the binary cross entropy loss. Okay. That is the negative y log y hat, negative 1 minus y log 1 minus y hat,
Yes, one word.
where this y hat denotes the probability for the class 1. With what probability my network has produced it for the class 1. As mentioned earlier, that in the output neuron for the binary classification, we use sigmoid activation. Okay. That value of the sigmoid will be basically fed into here. Okay. Now, because of our label, in general, we take the binary classification label is 1 and 0. Okay. This above function, if you see its shape here, if my label is 1, okay, then what will happen? This term will become 0 because 1 minus 1 is 0. Okay. And because y is 1, so it will be just negative log y hat. Okay. The base for the logarithm is the exponential. Okay. We use the natural logarithm here. If my y is 0, then the first term of this function becomes 0. The second term, 1 minus 0 is 1 times log of 1 minus y hat. Now, y hat was the probability for my network to output it as 1. 1 minus y hat will be the probability for it to output it as 0. Okay. So it is log of 1 minus y hat probability, negative log of 1 minus y hat. Okay. So basically this above function, okay, can be summarized directly as negative log y hat, where this y hat here represents the probability for true class. Okay. So if your data point has the class 1, then you are going to just directly use y hat here. If your data point has the class 0, then you are going to use 1 minus y hat value here. Because sigmoid always output it as, or we always consider the case that sigmoid output will be the probability for class 1. Yeah. Any doubt here?
So why it is y predicted, right?
Y predicted.
Y hat means y predicted.
Yes. Yeah. Probability. probability, or basically the output of the sigmoid function. Whatever the output of the sigmoid function you are going to get, that value.
So y is true and y hat is predicted. That's like,
Yeah, y is true label here. Y hat is the probability value.
which we got.
Yes. Yes, Shubham.
So like the one you have done, this basically the loss function will be used for that gradient descent theorem, right?
Yes. To update
So
the
like,
wait.
yes, for that, if then it will repeat the steps of the whole neural like the whole network again and again, right?
Yeah.
Okay, fine.
Okay, now it's not like we cannot use the squared loss in the binary classification. You can use that, but that's not an appropriate choice to start with. Okay, and it's not like we should only stick with the binary loss entropy. That's the only loss that we can start, but that's the good started loss function. Okay. Now for the multi-class classification, it's just the extension of a simple classification problem. Just like softmax was an extension for the sigmoid, we extend the case of binary classification problem loss function. Okay, that was the binary cross entropy to a general cross entropy function. Okay, in which it will be again just the negative log y hat, where y hat would be the probability for the true class. Okay, so as there are, let's suppose 3 class here. One thing here that this dotted line here does not have any meaning. Okay, I just used them because in that case it was looking much good. Okay, otherwise it will be very deep network, so it will not look good. Okay, they do not have any meaning here, these dotted line. Okay, so this y hat here is the probability for the true class. I have 3 classes here, 1, 2, 3. Okay, whichever is the true class for my data point, input data point. Okay, I will use the probability for that class, and I will put that probability here and calculate the loss. Again, let me write the softmax one. Okay, it's if I have the output of this layer network after doing the linear transformation, if I got the output something as 7, 5, and 3, okay, then if I apply the softmax on it, it will be like e power 7 divided by e power 7 plus e power 5 plus e power 3, and e power 5 divided by this summation again, and e power 3 divided by this summation again. Okay, the summation, same summation that is there. Okay, this is for the normalization, so that all of these probability of all of these elements should sum up to 1. Okay, and whichever, let's suppose if my data point has the true label of 2, okay, then I will use this value to calculate the loss.
So can you please explain this bottom part again?
Yeah, sure. So the multi-class classification, we just do the extension of what we were doing it in the case of binary classification. The only thing is we changed the activation from sigmoid to the softmax. Okay, as we have multiple class, so let's suppose the output of this layer network neuron that you got before applying the activation is 753. Then you will apply softmax activation, that is just e power of the element divided by the summation of e power of all the elements. So for example, for this case as an example, it will be first element will be transformed as e power 7 divided by e power 7 plus e power 5 plus e power 3. Second element is e power 5 divided by this entire summation again. Third element, e power 3.
Thank you.
Now, if my data point has the true class as 2, okay, then I will use this quantity, whatever this probability comes out, to calculate the loss. Okay. Now there is a difference between the value used for calculating the loss and the predicted value or the predicted class, because the predicted class, again here it will be following the same method, that among these elements, whichever got the highest value, that will be the predicted class. Suppose if the first element got the highest value, okay, then that will be the predicted class. Okay, that will be the one. But for the loss, because I'm assuming that like second is my true class, I will going to use the second class value here. Okay. Till now, is it clear?
We have to choose only one out of these three, e to the
Yeah.
power 7, e to the power 5, or e to the power 3, and all this sum to 1, as we already know that.
Yeah. Now, that is only possible if you are using the one-not encoded vectors for the multi-class classification. One-not encoded means if your classes are represented here as this 0, 1, 0, that means 1 here represents second class. Because from the above case, as seen here, okay, every other element will become 0. Okay, only the place where we have the true class, it will be 1. So that's why this long formula for the cross entropy is just shrink to this small value here. Okay, if you do not have this representation, that is basically one of the regularization methods. I'm not sure whether we are going to study that in our course, but that is called as that injecting error at the output layer. Okay, so in that case, what we do is we change this one-not vector into we add some kind of error here. Okay, so in that case, this formula cannot be used because we'll be having different values other than the 0. Then you have to go back to this big formula. And for the multi-class classification, it will be like the summation of y log y hat. And this will be summed across all the classes that you have. So if let's suppose you have some error like ABC. Okay. In place of 0, 1, 0, if you have ABC, then it's like A times log of the probability for this class, that is this value. Okay. Plus negative wave sign will also come. B times log of this value plus C times log of the third value. You will sum this up, multiply it with the negative sign. That's the final loss. Okay. If you do not have this one-not representation, if you have, then it is just simpler formula this. But if you do not, then you have to go with this formula.
If we have, then?
If you have, then you can just go with this formula, simpler one.
And in this formula, what we put like?
In this formula, you are just going to put the probability for the true class. Okay. If your true class is 2, then you are just going to put this quantity.
Okay, that's simple. One term.
Yeah, one term.
Instead of all these 3 terms.
Because all of these become 0 here. Okay.
Okay, got
it's the same function. It just said because of a simpler representation that we are using here for the class, that's why it's shrink down to this term. Yes, Priyanshu.
Sir, why would you want to inject error overcome overfitting?
Yeah, it's a regularization method.
Okay, sir.
I'm not sure we are going to cover this in our course, but it's one of the methods. In that case, we have to again go back to this formula.
But sir, that is specific to neural networks, like injecting error, because I think
you can do it for any
traditional ML.
In that also you can do. Okay. So some of the regularization methods are like you can do it anywhere, but some of them are only limited to the neural network. Like the dropout is something that is for the neural network case. So this loss functions are clear. Okay. Okay. Now comes the black house for the neural networks. Okay. We have done the forward pass based on some random initialization of the weights. Then we got the output where we have calculated the loss. Now times to go back and update these weights. These weights are getting updated using the gradient descent method. Now we have seen the gradient descent many times before. We started with from maths to then MLF, MLT. Okay. Now again we have this in DLJNA also. You will be again seeing this in DL or maybe in the LLM also. So as we have seen it multiple times, who is going to tell me about the gradient descent?
Sir, we have initial weight and we also have like eta and this learning rate. We have like this. So we converge, to get a global maximum or like minimum and global minimum, so that not global. We cannot say obviously that can be local minimum. Huh? So we try to achieve that minimum. That's our main purpose, and get in this.
Okay. Yes. So, but you told it like an overview, but how you'd perform the gradient descent?
Initial weight. I need to check. Initial weight minus neta, or then differentiable function like that.
Okay.
Sir, we take the gradient of loss function.
Okay. Yeah.
And
then how?
accordingly update the weight parameters.
We are also multiplying with the learning rate.
Yeah. Why we multiply with the learning rate?
For convergence.
So for convergence, yes.
Okay. Yeah. So. Okay. First of all, tell me about the direction of the descent. Is it in the direction of the gradient or in the opposite direction?
Opposite direction, sir.
Opposite. Okay. So the direction of the gradient is basically the ascent direction, or basically the direction in which the function value increases. Ronak, please mute if you do not have any doubt. So I will use some things that we studied in maths too. I hope you guys recall. So to take the directional derivative, okay, for any function, if you want to take the directional derivative, if it is a differentiable function, okay, especially if it is a multivariate function, you are going to take the gradient and you are going to multiply, or basically going to take the dot product, okay, of this with the unit vector. Okay, unit vector is basically the direction in which you are calculating your directional derivative. Okay, so I hope you guys remember this. So this was for the directional derivative part. Okay, now because this was a dot product between these two vectors, dot product between two vectors can be represented as right, the angle between the two vectors on which you are taking the dot product can be represented as A transpose B divided by norm of A times norm of B. So if you are taking the dot product between these two vectors, you want to find the direction along which my function value increases mostly or that decreases mostly. Okay. So for that, if I'm going to check the angle between my gradient of the vector, gradient of my function and the direction vector, and that is cos theta equal to gradient of f transpose u divided by norm of the gradient of f times norm of u. Because we consider u as a unit vector, this will basically becomes 1. Okay. And what you left with is just this value times the unit vector. Okay. Now this is a normalizing factor. Okay. So you can say that the cos theta is proportional to the gradient of f transpose u. Okay. Now because cos theta function is bounded between 1 and 0, sorry, 1 and minus 1. Okay, minus 1 and 1, where the maximum value occurs at the angle of
0.
1. Cos 0 is 1.
Yeah. Okay. So at the theta value to be 0, okay, that is the angle between the gradient of the function and the unit vector is 0. Basically, both are pointing in the same direction. My cos theta value is maximum, that is 1. And when my theta is what, then my value would be minus 1. At what?
180.
Correct. 180.
Yeah.
At the 180, that is in the opposite direction of my gradient. Okay. So if my unit vector is in the opposite direction of the gradient, then its value is the lowest. Okay. That's why we say that descent direction, or basically the direction in which my function value decreases, is the opposite of the gradient. The direction in which my function value increases is the direction of my gradient. Okay. Now, okay, so this was a fact. Now, the algorithm, how we design it is, we'll be starting with some initialization of my weight vector or the weight matrices or anything you have, okay, with some random vector. Okay, in the starting course of the Maths 2 and MLF MLT, we generally initialize it with the 0. All weights are initialized to 0, but actually it is not a good practice to initialize everything with the 0, okay, because it can make the convergence slow and it can create some other problem also, like the problem of dead neurons and something. Okay, that's why it is always good choice to initialize all the weights and bias, or basically all the parameters, randomly. You can sample from a normal distribution, and using that you can initialize all the parameters that you have randomly. Okay. Now here, let me remove the theta, W and call it as theta. Theta is basically the collection of all the weight metrics and the bias that you have. Okay, so I'm collectively storing all those parameters and calling it as theta. Okay, and so first step is the initialization. The next is you are going to run the algorithms, and in each iteration you are going to update the parameters as theta t, that is the current iteration parameter minus the gradient of my loss function with respect to theta. Okay, so and we also use this learning rate here. Okay, now the reason for the learning rate, we do not want a full update with respect to the gradient. We want to move with some step size or with some fraction in that direction. Okay, so use the learning rate. Yes, Shubham.
So like basically in every case the eta or the learning rate is basically experimental, right, sir?
Yes.
Okay, fine.
It is also a hyperparameter. You have to adjust its value many times because there are many problems with respect to theta, sorry, with respect to the eta. Okay, and that's why a different type of optimization problems, optimizers comes. This was a vanilla gradient descent version. In our course till now, we have seen two more types, the batch gradient descent and the stochastic gradient descent. But there are few more like momentum based Nestrov, then RMS prop. Okay, Adam, that sir is used, but so far we have not discussed the Adam in the lectures. Okay, those basically try to adjust these learning rates efficiently. Okay, so they all revolves around how we can more efficiently improve the optimization and the convergence.
Sir, we also use something like, some limitation like till 5 parameters. If there is not much change, then stop
Yeah,
this process like this.
that is one of the regularization technique that is called as the early stopping. That if some number of patients iteration you will set, if by that time your loss is not improving or accuracy is not improving much, then you can stop the learning, or maybe you can decrease the learning rate or try to increase it. Okay.
Yeah.
So that's the early stopping. Okay, so for now the simple vanilla gradient descent is you are going to update your parameters as follows. The current parameter value subtract with the negative sign comes because we are moving in the negative direction, opposite direction. Okay, eta is always a positive value. Okay, eta is greater than or equal to 0. Okay, and this is the gradient of the loss function with respect to theta. Okay, now comes the few variants of the gradient descent, that is the mini batch gradient descent and the stochastic gradient descent. So who can tell me about these two? I think STD we have learned in the MLT and in the MLP. So STD, anyone? How many minutes to take? We have technically few more concepts to do. So if you all are okay, we can extend the session for half an hour more. Then I will be able to cover the theoretical part at least fully.
That's fine, sir.
Okay. Yeah. So SGD, anyone knows?
Sir, in SGD, stochastic gradient descent, we are just calculating a gradient descent on the batch wise. We just divide the data points into in a batch wise. And
What is the batch size in that case?
batch type.
One record
Batch.
after every record.
Sorry. I was not able to hear you. What was the batch size you mentioned?
One.
Batch size of one.
One.
So after every record, you update the parameter.
Yeah. Basically, you will only be taking one data point in one iteration. And using one data point, you are going to update your parameters. Okay. So let me discuss two terminology here. One is the epoch. Second is this iteration or the number of times the parameter update. Okay. Now, epoch is something that we say that it's one full iteration over the data set. Okay. So we will say that we have completed one epoch when you have fully seen one, you have fully gone through the entire data set once. Then that is considered as a one epoch. An iteration or number of times the parameter update happen, it's basically your iteration. Okay. So in SGD, because you are updating your parameters with respect to each data point, in one epoch, the number of times the parameter update will happen will be equal to the number of data points, right? Because one epoch is basically one full pass over the data points. Okay. And because in SGD, we take one data point at a time to update the parameter. One epoch, the number of updates that will happen in SGD is the number of data points. Is this statement clear?
Yes, sir.
Sir, I'm not able to understand. Can you please?
Yeah. So as first, this thing was clear. What is epoch? It's one full pass over the data point. Okay. What happens in the vanilla gradient descent? You are going to take the entire data set. You are going to take that gradient and you are going to do the update. Okay. So in the gradient descent, the epoch and the number of updates that happens is basically same. In the SGD or the stochastic gradient descent, because we take one data point at a time to update the parameter.
In vanilla also, we are taking one data point at a time, right?
No. In vanilla gradient descent, we take entire data set.
Qt plus 1 equals to, sorry, theta t plus 1 equals theta t minus theta, something like.
We are
So
taking
you
all
can
the
say that
parameters.
we are
This
taking.
gradient is calculated with all the data points.
Okay, this term,
Yes.
neta gradient descent, like this one.
Yeah.
So
Here
there
the
is a
gradient,
change. In stochastic, there is a change.
yeah. Yeah. In the stochastic, you are just going to use one data point. You pass it to the neural network. You will get a loss value. Based on that loss value, you are again going to do the backward pass. We'll see it later how you do the backward pass. Okay. And using just that one data point value, you are going to update the parameters. In the vanilla gradient descent, you are going to do the forward pass fully. You are going to do the full loss computation. That is just the sum across all the loss values. Okay. And then do the backward pass to update the parameters. Here you
Okay,
are
and
only going, yeah.
and what exactly the epoch is like?
Epoch is one full pass over the data set. That is, once you have covered the data set entirely once. Okay, you started with x1, then you went to x2, then you went to x3 till xn, the number of data points. When you complete this one full pass over the data point, that is called as epoch.
So what its significance, like what's the significance of this?
Here I was just telling the difference between the epoch and how the parameter updates happen. So in the vanilla gradient descent, in one epoch, that is in one full pass over the data set, the number of updates will be same as the number of epochs. While in the stochastic gradient descent, because you are going to use one data point at a time to update the parameter. in one epoch, that is one full pass over the data points, you are going to update your parameters n number of times, right?
Yeah.
Because you have n data points. So in one update, in one data point, one update will happen. Okay, so in one epoch, that is one full pass over the data point, the updates will happen n times.
Yeah.
Okay, that's what I was telling.
Okay, sir.
Okay, so in one epoch, n times.
And that iteration also, like,
Iteration is basically, as I said, the number of times the parameter update. So basically these, the T
this
subscript that is,
update.
yeah,
Got it.
this update. Okay. So now comes mini batch gradient descent. Okay, so in the STD, we were just using one data point at a time. Now, because the loss functions was calculated using only one data point, the parameters are also getting updated using one data point. The updates that were happening were quite noisy. Okay, because each time the parameters are only getting updated with respect to my current data point. Like, how can I make my current data point classified better? Okay, so that's how the updates were happening. So that's why they were quite noisy. Okay, and to overcome that, we have this mini batch gradient descent. Okay, the only difference is that instead of taking one data point, we take a subset of the data point. So if you let's say 1000 data point, you can set the batch size to be 100. So in one parameter update, okay, that is in this one iteration. Previously, you were using one data point to calculate the gradient. Now you are going to calculate 100 data point to calculate the gradient. Okay. So
yeah, got it, sir.
use a batch size. So suppose if you have 1000 data points, your batch size is 100. Okay. So in every iteration, you are only going to use these 100 data points to update the weights or the parameters. So in one epoch, how many times the parameter will get updated in the mini batch
10
gradient descent?
updates.
10 updates. Very good. Okay. So for this example, one epoch, it's basically n by b param update. Okay. So are these three methods clear? Vanilla gradient descent, stochastic gradient descent, and the mini batch gradient descent.
So mini batch is better, right?
Yeah, mini batch is much better.
Because instead of calculating all or one, we are taking the middle path. Like,
yeah.
Oh, got
Basically, stochastic is just you set the batch size to be 1. That's basically the stochastic one.
Yeah.
So it's one of the same table that Prof has used in his lectures. Okay. So
Yeah.
data is batch gradient descent. Oh, sorry, I think batch GD. This should not be batch GD. It should be vanilla. Yeah. Okay.
So like the normal the vanilla GD is a normal GD, right?
Yeah, normal gradient descent.
Okay.
So in the normal gradient descent, you use the entire data set. In the STD, you use one example at a time. In the mini batch, you use a small batch size. Okay. The speed, vanilla gradient descent is slow because it is using the entire data set. So if your data set is very large, it will be computationally heavy. Yes, Saurabh.
Sir, by taking a subset of points, how the noise are getting reduced?
How the noise are getting reduced? See, in the SGD, what was happening is we were using only one data point, right? So every time the update was happening with respect to the current data point that I'm using. So every time what was happening, like my gradient descent algorithm was trying to update the parameter in the favor of the current data point that I'm using. That I want to classify this data point correctly. So that's why they were quite noisy. If we take a mini batch size, okay, then because we will have more data
What
points
do
to
you
look
mean by
up.
noisy?
Noisy means the how the updates are happening. So okay, so Do you know about the contour plots?
To some extent.
To some extent, okay, I think that will suffice. So contour plots are basically the representation of a 3D figure into 2D. Okay.
Yeah.
So suppose this was your like contour plot for a squared function. Okay. So in the 3D, it's like a ball shaped figure, and that's why in the 2D, it's like more circular shape. Okay. Now, in the case of a smoother convergence, it can simply like converge to smoothly, right, to the global minimum. Okay. But in the case of noisy updates, it's like quite up and down, up and down. Okay. It will not be this much, but it will not be just smoother convergence like a vanilla GD. Okay. So it will be like quite noisy. The updates will not be smoother. Okay. That's what it means by noisy.
So how does it affect our overall model? Like if even if it's like ultimately we are converging, right? Our motto is to converge, right?
So you
Ultimate
do
goal
not
is
know when the convergence will happen, right? In
that's
the like for a smaller figure size or smaller dimension, you can know, but for the higher dimension, you cannot visualize it. So if the
and
updates are noisy, then you can might be stuck at somewhere where it's not an optimum place.
so n epochs means n times. So like there will be a lot of data, so lot of noise.
Yeah.
Got it.
Okay. So that's it. Now, in the case of mini batch, it's moderate and fast. The speed is depends upon how you choose the batch size. Of course, if you set the batch size to be entire dataset, then it's basically the vanilla GD. Stability in the vanilla GD, of course, it is smooth because it's using the entire dataset. So of course, it will be the smoothest among all. For the stochastic gradient descent, it will be very much noisy. Mini batch, it will be smoothly compared to the stochastic one. Of course, it will be also not perfectly smooth like the vanilla GD, but compared to SGD, it will be quite smooth. Okay. Now the GP uses, that is the main purpose of using the PyTorch library that we use. Okay. In the vanilla, it's very poor. If you have a large data set, it will be computationally heavy. SGD, it's efficient. Mini batch, it's very efficient because it will be smoother updates. Okay. And you are using a batch size of the data points, so your updates will be smoother, not noisy. Fast updates will happen. Okay. So overall, we generally go with the mini batch gradient descent. Okay. While updating the parameters. Okay. So any doubt here? Okay. Now comes the final part, the backpropagation algorithm for updating the parameters for the neural network. Now the main idea the backpropagation uses is the chain rule in action. Okay. So if your calculus part is good, okay, you should not have any problem in understanding this, specifically the chain rule. Okay. So a good revision of the chain rule is if we have a layer of affection here that is happening. So suppose you have a variable y for a variable x that affect your variable y, and y affect then your z. Okay, and you want to calculate how my z is getting affected by x. Okay, then you have to backtrack it that how my z is affected by y and how y is affected by x, because x directly not affecting my z, x is affecting y and y is affecting z. Okay, so as that this is a chain of network that is happening here. Okay, the derivative that will happen will also conclude this step that I will first calculate that what is the derivative of the z with respect to y. I will multiply it with how my y is getting affected with x. Okay, and this chain rule can also extend to multiple layers of network that we have seen above. So for the starter, let's start with this simple loss function. It's not also a loss function, it's just a simple function you have. X plus y into z. It's the same example that Prof has taken in the lecture. I think it was just a plus b into c in the lecture. So tell me first, if I was want to take the derivative of z, okay, let me write this as plus y into z. This is equal to some. If I take the derivative of this loss function with respect to z, what will I get?
X plus
y.
X plus y. Okay. Now what about this? What will I get?
Z.
Z.
Okay. What about this?
Z.
Z. Okay. Now first for the one layer. I list this plus y z. Okay. So I think this will not be. Let me take some other function. Square and y is okay. So I have one function x plus y square and y is 5x square. Okay. Now if I want to take the derivative of loss function with respect to x, how it will be? I can write either this y as this. Okay. So it's like a chain rule here. Okay. First you have this outer squared function and then you have the x inside them. So what will be the derivative now?
Multiply by x plus 5.
Sorry.
Two x plus 2y.
2 into
X plus y.
X plus 5.
Plus 5x square.
Then it will get multiplied by
Into 1 plus 10x.
1 plus 10x. Okay. Yeah, that's all. Okay. So as we have this outer squared function, okay. So first we will take the derivative of the outer function, then we will multiply it with the derivative of the inside term that we had. Okay. So that's how you do the chain rule. Okay. It was a simple example. So basically same thing we will be doing in the forward pass for in the back propagation for the neural network also, because here we are doing a chain of linear transformation and then activation. Okay. So let's first start with simple connection here, that we have the x as an input. Okay. We are multiplying it with y. Sorry, we're multiplying it with w. We'll get w transpose x, and we are applying sigmoid function on that. Okay. And my loss function is binary loss entropy, negative log y hat minus 1 minus y log 1 minus y hat. So this is my loss function. My y hat is this sigmoid of w transpose x. I want to update my weight vector w. Okay. Everything here is a scalar value. Okay. So we do not have to worry about the vector in the matrix. We'll look at that case later. So how we are going to start? First, as we want to update w. Okay. So how that w affect my loss function? It's multiplied with the x, gives me this some value. Then on that value we apply the sigmoid function, and that's how it affect the loss using this function. So what should be the first step that we should do? We have to calculate the gradient of the loss function with respect to y hat.
Y hat.
Because w affect this sigmoid function, and that sigmoid function output will affect my loss. Okay. So the sigmoid function output, that is y hat, that is directly affecting my loss function. So first you will find how this y hat affect my loss function. Then I will multiply it with how my y hat is getting affected with this w here. Okay. Yeah. So first, this quantity, gradient of loss function with respect to y hat. What will be the loss? What will be the derivative for this quantity with respect to y hat?
So -1 over y hat.
-1 over y hat. Then here also we have y hat, right? So what will happen? Just like you did the derivative of this, same thing will happen here, right? Negative 1 minus 5, that's the constant value, so it will just be there in the sorry.
So it should be minus y upon y hat.
Yeah, so it is minus y by y hat.
Minus y upon y hat plus 1 minus y upon 1 minus y hat.
Yeah, correct. Plus will happen because of this negative sign here.
Negative sign, yes, sir.
Yeah, very good. It's correct. Okay. So this was the derivative of, or basically
Loss
this was
function.
with respect to y hat. How my y hat affect my loss function. Now, because we are basically trying to find here how my weight affect the loss function. So weight affect this y hat using this equation. Y hat is sigmoid of W transpose X. Okay. So if we go back in the layer, we have to take the derivative of this sigmoid function next. Okay. So what is the derivative of the sigmoid function?
F of x into 1 minus f of x.
Yeah. Okay. And f is basically what? This y hat here. Okay. So, if you do not remember, the derivative of the sigmoid function for any z is sigmoid of z into 1 minus sigmoid of z. Okay. So I will multiply this quantity here with y hat into 1 minus y hat. Okay. Now let's move more in and forward. So the outer part done, then the sigmoid part is done. Now we have access to this W transpose X. Okay.
Sir, how you got 1 minus sigma z?
This you mean?
Yeah.
It's you can try taking the derivative of the sigmoid function that you have. Okay. The sigmoid function is this 1 upon 1 plus e power negative z, right? You have to apply the division rule here. Okay. In that case, you can try.
What formula you applied? Like
here, it's the derivative of the sigmoid function. It has a very nice form.
Okay,
Sigmoid.
derivative. Got it.
Yes, Shubham.
So basically, like as you have told that we are doing the back propagation only to track the things, but is it generally like is it updating the anything value like in the main part of the convergence or something else?
We are updating only weights. We are not going to
But
update
that
anything.
is through the gradient descent algorithms, right? But why are we using back propagation?
Back propagation is called this entire algorithm that uses gradient descent rule to update the parameter. Back propagation because as we are doing the forward pass, so we pass the values to the network and got one output. Okay. Now we are back propagating. Yes.
Yes, sir. So basically, this is a like the part of the gradient descent explanation only, right?
Yeah. Okay.
Sir, is it right to say we are updating weights in both direction, first and forward, and then back propagate?
No. In the forward pass, you do not update the weights. In forward part, you just calculate the output. The updates happen in the back propagation only.
Only in back propagation, sir.
Yeah. Okay, so let's come back here. The y hat part done. Okay, you have calculated the gradient with respect to sigmoid also. Now we have access to this entire quantity W transpose X. If you are going to take the derivative of this with respect to W, what you will get? X. Okay, so multiply it with X also. Okay. Okay, so let me so loss function was negative y log y hat 1 minus y log.
So why you are taking this loss function? We can take the regression also.
Yeah, you can go with the regression also as starting with the classification part. Okay, so you can start with the regression also, no problem in that. It's just that in the regression you are not going to take the derivative with respect to activation because the regression for the output you just use the linear activation. Okay. So because we are going to include the activation further on, so that's why I started with the classification part.
Okay, thank you, sir.
Okay, this was for the y hat. Then we take the y hat derivative. So let me call some quantity here. So
It is
the
y
W
hat.
transpose X, we were using it as Z,
Yes.
like the pre-activation. Okay, so a bit of Z. That was the y hat into 1
Y
minus.
hat times 1 minus y hat.
Then derivative of this Z with respect to W, that was the stacks. We have to multiply these three. Let's first simplify this quantity because here some good modification will come. So it's y hat into 1 minus y hat in the denominator. In the numerator, it's negative y 1 minus y hat plus y into y hat into 1 minus y. Okay. Okay. Now, if we multiply these two quantity, okay, this y hat into 1 minus y hat will cancel out this denominator, right? Okay. So we're left with just this numerator. So I'm just copying that part. Negative y into 1 minus y hat plus y
Hat times 1 minus y.
Okay, if I simplify this,
We'll take
negative y
negative y plus y hat.
these two again will cancel out. Okay, so in the final output you will get y hat minus y. Okay, and then I have to multiply it with this third quantity also, x. Okay, so finally the derivative of the loss function with respect to weight comes out to be this y hat minus y times x. Okay, it has a very simple good representation. That is basically you are calculating this error part, kind of error, y hat minus y, and multiplying it.
Negative error.
Yeah, it can come negative also. It can come positive also because depends upon your label. If your label is 0, it can be positive. Okay, so it's kind of an error times the x. Okay. Now, one good thing about this terminology, this term y hat minus y, is that with most of the loss functions, okay, especially if you are going to use the binary cross entropy function with the sigmoid at the output layer, okay, then the derivative of the loss function for the pre-activation stage, that is still z, okay, will always comes out to be this error term only. Okay, so if I repeat what I was saying, that for most of the time the derivative of the loss function with respect to the z at the output layer, okay, will always be this y hat minus y for most of the time. Of course, it depends upon the structure of the network and what type of activation function you're using. But if you're using binary cross entropy function, okay, and output is the sigmoid one, output activation, then also it will be same. If you are using cross entropy function again, and for the output layer, if you are using softmax regression, then also the derivative of the loss function with respect to the output layer pre-activation stays. In that case also it will be y hat minus y. I'm not going with that calculation because that involves the calculation of derivative with respect to softmax. That actually involves the Jacobian matrix. So that's why I'm avoiding that part. But in that case also you are going to get the same derivative for the output layer reactivation stage. Okay, till that part only it will be.
Would it will not be multiplied by x? It will be just
Yeah,
y minus y.
no, it will be multiplied. I am just telling that till the ZL. Z represent the pre-activation stage. L here represents the output layer or the last layer. Till that part I am saying. That is, suppose if you have a network like this, okay, and you can have this also. Okay, so I was just telling that if you are using a softmax softmax activation in the output layer, and you are using a cross entropy function. Okay, then for the output layer pre-activation stage, okay, that is the ZL, or basically for this it will be Z2. Okay, L I am representing for the last layer, okay, or the final layer. For that I was telling
So
that
when you say pre-activation, what does it mean? It is without taking any output from the layer.
pre-activation means I am not applying the activation so far. So it will have two part, right? Every layer will have two part. One is the Z2, the another is A2. A2 is after we apply the activation. Okay, and then that A2 will be used for the final loss computation here. Okay, is it
Sir,
clear?
I did not actually. I haven't understood fully, but I will check. I mean, I will go through the slide.
It's the same thing that we discussed here, right? At the time of forward pass, that for each of our forward pass case, we will be having two stages. One is the pre-activation stage Z1. Another is after we apply the activation A1. Okay, so we will keep doing this linear transformation. You will get a Z1. You apply the activation, you get A1. Then you will again do this linear transformation. You will get Z2. Apply activation, you will get A2. Keep following this. We will reach till this point, Z3. Then after applying the activation, you will get A3. This A3 will be used for computing the loss function. Okay. Now what I am telling is, for the derivative of the loss function, if you are using cross entropy with either you are using the sigmoid activation at the output layer, that is at this part, or either you are using the softmax regression, or sorry, for the softmax activation. In both the case, the derivative of the loss function with respect to Z3, okay, that is the pre-activation stage, will always be y hat minus y.
Okay, sir.
We did it here for one case. That was the simple case in which okay, you have just one neuron in the input, one neuron in the output. Okay, but you can try. It's the same thing that will happen even if you have a multiple stack of neurons. Okay.
So I'm not able to understand the context of this back propagation. Like, I think we have to study from other sources also to understand fully.
Okay, let me
It's
take
a
this one
complex.
more example. Let me take this one more example because this includes one
Yeah,
chain of
please,
network. Okay.
please.
So here we'll start with this x. Okay. We'll multiply it with w1, the first state vector. We'll get z1. Okay, let me do so. So this half filled represents two states, pre-activation and after activation. So Z1 denotes the pre-activation, just the multiplication of my input data point with the weight. Okay, I'm skipping bias here for now to simplify the calculation, but we can add the bias later on, okay, for now. Then it will have this A1, that is after applying the activation. Then we will have another weight W2. we'll get Z2, A2, and we can apply it W3, Z3, A3. This A3 is the final output for my neural network here. Okay, or for this simple chain of network. And that A3 will be used for the final computation for the loss function. Okay. Now, as somebody said, like previously we used the cross entropy loss for the binary classification with sigmoid activation. Let's suppose we take this time the regression case. Now in the regression case, as we do not apply the activation at the end, it's just a simple linear activation. Okay. So before that, let's first do the forward pass. The forward pass equation, if I write, Z1 is W1x. Okay. A1 is sigmoid function. Let's suppose I use Z1. What will be Z2?
W2 times A2.
A1.
A1.
Yeah. Okay. And A2 is sigmoid
of Z2.
Okay. You can use any other activation function also, but most of the time the process will be same. Yeah. Or every time it's the same. Then Z3, it's W3 A2. And A3 is for now it will be Z3 only because we are using the linear activation for the regression. For regression. For classification, if we are using the sigmoid activation, then A3 is sigmoid of Z3. Okay. These are the forward equation. Now let's try to do backward pass for backpropagation on this.
So A3, Z3, why you like taken? Like for A2 and A1, you have not taken any regression.
Yeah. So see, there we wanted to introduce non-linearity. Okay. But here we want the output. For the regression case, the output can be any real number, right?
Yes.
In that case, if you are going to apply any activation, the choices of activation that you have. Sigmoid, it will just bound the output between 0 and 1. tanh, it will bound the output between -1 and 1. ReLU, it will also just squeeze everything to positive side. Parametric ReLU, it's not, it can take, but it's going to be very slow for the negative case. Okay. Same for the other case also. So
yeah. So my question is, for A3 we are taking the Z3 for regression, okay? But for A1 and A2 you are not taking any regression, so that's what.
Regression. See, it's not the regression. It's the choice of activation function we are using. Here we are using the identity activation function. Identity means it's just the same value.
So why you're not taken for A1 and A2 like this?
Because there we wanted to introduce non-linearity.
Okay.
If you are going to use it there, okay, then it will be same as the linear regression case, because if you do not include the non-linearity part.
Then how it's changing in A3 then?
Because here we are using the non-linearity part.
Okay, sir. Yeah.
Yes, anybody has any doubt? Somebody knows in between?
No, sir, it was actually by mistake. I raised my hand.
Okay. So far are the forward equation here. For the regression case, as we are not going to apply the activation because they want the output can be any real number. Okay, that's why we are not using it here. For the binary classification, you can use the sigmoid activation function. And this A3 will also be your y hat here. Here also it will be y hat. Now let's move to the backward pass equation. Yes, Priyanshu, any doubt?
Sir, can you, in the neural network architecture that we saw earlier in the earlier slide, so can you relate to this? I mean, back propagation, because in this you have taken this separately, right? So how to visualize from that?
Which one? The first one?
Yes, sir, the bigger one, the initial one that we have.
I'm not using that because this will involve the derivative with respect to matrix and vector.
Sir, I mean, without computing, if back propagation, if I have to understand, so basically this is, we are just talking about the first one, the top one, right? The top.
Yeah. So how the things will happen that this A3 will be used to calculate the loss. Then you have to compute these weights that are there, here and here. So first, because how this weight affect Z3, Z3 affect A3, then A3 affect loss. Okay. So we're first going to take the derivative with respect to A3, then derivative of A3 with respect to Z3. How my Z3 affect A3 and A3 affect loss. Then this weight, how this weight affect this Z3. So that's how the chain will work. This was for the first or this outermost weight. For this W2 that is there here, for this matrix. How this W2 works? This W2 affect Z2, Z2 affect A2, A2 affect Z3, Z3 affect A3, A3 affect loss. In the backward pass, derivative of loss function with respect to A3, derivative of A3 with respect to Z3, derivative of Z3 with respect to A2, A2 derivative with respect to Z2, Z2 derivative with respect to this weight matrix. Okay?
Yes, sir.
Yeah. Okay. Now let's do the backward pass. So for the regression case, what's that? Y hat minus y square. Okay, for the classification, it's negative y log y hat minus 1 minus y log 1 minus y hat. Okay. So let's not take two at a time. First, go with the classification case that we were doing it so far. Okay. So as we have to do with the backward, we have to start from the last side that we have. So that is this A3, because that is the part that directly affect my loss function. Okay. So first, just look at the classification equation. Okay, A3, Z3, W3, U, Z2. So how my A3 affect my loss function? We have already calculated that part, right? Gradient of the loss function with respect to A3. Okay, it was this negative y hat plus 1 minus y divided by
1 minus y hat.
Okay. Then how this A3 is getting affected by this Z3. Okay, that we have to calculate. So derivative of A3 with respect to Z3. Okay, if you look at the forward pass equation, Z3 was here. A3 was sigmoid of Z3. Okay, how you are getting A3 from Z3? It is after applying the sigmoid. So you have to take the derivative of the sigmoid function here. Okay, so it would be just A3 into 1 minus A3 here. Okay, is this part clear till now?
Yes, sir.
Okay.
So 1 minus A3 not clear, sir.
See, that is the reason. See, because we are using the sigmoid activation here. Okay, what was the derivative of the sigmoid? Sigmoid into 1 minus sigmoid.
Okay.
Okay, and we are calculating the derivative of Z3 with respect to A3. Sorry, derivative of A3 with respect to Z3. Okay, that's why here it will be sigmoid function of Z3.
Okay, derivative of that sigmoid function, got it.
Yeah. Okay. The later part multiplication we can do at the end. But what we basically want to update is this W3. So now we will look at this equation, that is Z3 equal to W3A2. Okay. So now you are going to take the derivative of Z3 with respect to W3. So what you will get?
A2.
A2, just A2. So derivative of Z3 with respect to
W3
W3
will be A2.
A2. Okay. Later you can multiply just these three quantities together. Okay. And okay, I am skipping the multiplication part. We will do it later. So that was the derivative of the W3. Okay. With respect to W3 for my loss function. Now, if the W3 is done, we'll move on to W2. Okay. I will just do it for W2. Okay. I will leave the how it will happen for W1 for you guys to practice. Okay. So it's the same thing that we are doing it so far. It's just that now you have to just go back a little more. Okay. So we have calculated how my Z3 affect my loss function here. That my loss function is getting affected using A3, then how A3 affect Z3. So if till Z3 is done, before Z3, this A2 comes. Because how my W2 affect my loss function, W2 affect Z2, Z2 affect A2, A2 affect Z3, Z3 affect A3, then loss function. Okay. So just keep this network structure in mind. The way the forward pass is flowing, in the same manner you have to flow it back. As W2 affect Z2, A2, Z3, A3, then loss. Then from loss to A3, from A3 to Z3, Z3 to A2, to Z2, then W2. Yes, Shubham.
Yes, sir. Like the flow you have told, that like we move in the forward pass, we will just reverse it in the opposite direction. Like as like in the screen, what I can see is that ultimately we will be getting DL by DW3. So it's basically says that if the change in the like change of L with respect to W3. So what does that mean?
So it means that how much should I change my W3? Then if I change my W3, then how much my loss will change? Okay, and we have to tune this parameter in such a way so that we can minimize the loss in the end.
So in this way, we will get also the W2 and the W1 also.
Yes. Okay.
So with this, all these three functions, we can like formula is a formula for this.
Yeah, you have the equations for the backward pass in
Yeah.
the end. Okay, we will write those equations for now.
Okay.
So, but for the starter that I told here that for the derivative of the, give me 1 minute, let me restart that. I can do it. Yeah. So for the starter, as I told here that we have this equation here. Okay. So for the derivative of the loss function with respect to Z3, okay, that was comes out this, right? Y hat minus Y. Because if you multiply these two quantities, you will get this part. Okay. And then for the derivative of the loss function with respect to W3, it would be just Y hat minus Y times A2. Okay. So let's move backward a little. Z3, A3. As this is done, now we have to go with this. So we already have this derivative. Okay, that is how my Z3 affect my loss function. So using that, we will move it backward. That how my Z3 is getting affected by A2. So how it affect we have to go with the forward equation that we have. That was this. Z3 was W3A2 plus bias term was there, but let's skip it for now. Okay, so if I want to calculate how my A2 affect Z3, that is the derivative of Z3 with respect to A2, what it will be?
Sorry, sir, can you please repeat your question?
Yeah. So see, we have calculated. Yeah, W3 is correct. So see, we have seen it so far, right? That how my loss function is getting affected by Z3.
Yes.
Okay, that was y hat minus y.
Yes.
Okay. So using which, if you just take the derivative of Z3 with respect to W3, that is just simply A2. Okay.
Yes.
Using this equation, you can update the W3.
W3. Yes.
Now we have to update the W2 also. So for
Yes.
that, we have to move it backward.
Yes.
So as we have already calculated till till Z3. Okay. The way we will move it backward is W2 affect Z2, Z2 affect A2, A2 affect Z3, and then so on. So we have to see how this Z3 is getting affected by A2.
A2. Yes.
So in this equation, we know how A2 affect Z3. So we'll take the derivative of that part here. That will be what?
W3.
W3. Okay. Later on, you have to just multiply this term, right? If you are just finding this term, that is gradient of the loss function with respect to W2, it's gradient of the loss function with respect to Z3, derivative of Z3 with respect to A2.
A2.
Then
derivative of A2 with respect to Z2.
Z2, then
derivative of Z2 with respect to W2, then W2 with respect to A1.
W2 will not take part.
Oh, sorry, sir. Yes.
Okay. We just want to calculate this till this. Okay.
So can I calculate like the change of A3 with respect to A2 or Z2 like?
Change of A3 with respect to A2.
A2
Yeah.
or Z2 or W2?
Yeah. It's just that you have to do the multiplication. How my A3 affect, how this A3 is getting affected by Z3, then how Z3 is getting affected by A2. That's simply the derivative of A3 with respect to A2.
Okay. So I know that Z3 equals to W3A2. So that I will get the derivative and I will multiply with, the next, the back, Z2A2 or something, whatever is there.
Yeah.
Like in this chain structured way.
So like in this chain reaction that you see, for which we are using to update the W2, we have this derivative of loss function with respect to Z3, Z3 with respect to A2, A2 with respect to Z2, then Z2 with respect to W2.
Why you not using A3 in this one? Del L by del W2.
See, we already have till this much. You can use it. In the end, see, this Z3 is how it is getting computed. The derivative of the loss function with respect to A3, then derivative of A3 with respect to Z3. But because we have already computed these two quantities, okay, that's basically the derivative of the loss function with respect to Z3. I'm reusing that instead of recomputing it again.
Oh, where you reusing that?
We are reusing it here directly.
No,
where have I
the
computed it?
One, yeah, the latest one you computed this below.
This one?
Yeah, del L by del W2. Yeah.
In this one, here I am using it. The first thing is this.
Okay, del L by del Z3.
Z3. Del L by del Z3.
So A3 is already inside this one, like.
Yeah. See here. First, we calculated the loss function derivative with respect to A3. Okay. Then the derivative of A3 with respect to Z3.
So it comes out to be del L by del Z3.
Yeah, if you do the multiplication of these two, it will be the del L by del Z3.
Okay, sir.
Okay. That's what we did here in the single chain network that we talked about here. Okay. Here, that's what the same thing where you are doing it. Right. First, we take the derivative of the loss function with respect to this y hat. Then the derivative of the y hat with respect to this inner quantity that we had. Okay.
So we already know the activation function value, right? Like A equals to sigma of Z3.
Z, yeah. Because in the forward pass we know it, what we got.
Yeah. Through that we're gonna find the Z, something like, so like This way we are doing, right?
Yeah. First step is to do the forward pass. Only then you will get these values Z1, A1, Z2, A2. Then using that we will go to the backward pass.
Okay, sir.
Okay. So let's just follow this chain. Okay. This part was done here. This part was also done here. Okay. Now next is what? Derivative of A2 with respect to Z2. Okay. Now can you tell me what it will be? Derivative of A2 with respect to Z2. Remember the forward pass equation.
A2 times 1 minus. No.
Just remember how I got A2 from Z2. How you got it, and from that you will be able to do it.
No, the sigmoid. No, you have to put.
Sigmoid derivative.
Yeah, correct. So what you were telling is was correct, that A2 into 1 minus A2.
Yeah, you have to do that.
If you look at here, this was how the forward pass calculation was done. A2 is sigmoid of Z2. So if I take the derivative of A2 with respect to Z2, it is just sigmoid of Z2 into 1 minus sigmoid of
Z2.
That is simply A2 into 1 minus A2 also. Okay. So the derivative of the loss, not the loss, A2 with respect to Z2 is A2 into 1 minus A2. Okay. Now with that done, last part, derivative of the Z2 with respect to W2. Remember the forward pass equation and tell me what it will come. How I get Z2 using W2. Remember the forward pass.
Z2 is W2 times A1.
Yeah, correct.
Just A1.
So
A1.
A1.
Very good. So this part is just A1. Okay. The only part that is remaining now is just you will multiply these four quantities. Okay. So this was y hat minus derivative of loss function with respect to W2 is loss function derivative with respect to Z3. Z3 with A3. A3 with sorry, not A3. A2. A2 with respect to Z2. Then
Z2 with respect to W2.
This part was y hat minus y. This part Z3 with respect to A2, we have got it somewhere. Yeah, here. W3. A2 with respect to Z2.
A2 1 minus A2.
A2 minus. Then this quantity Z2 with respect to it. A1. Okay. This was for updating W2. So this was for W2. Now you can again go back more to update for W1 also. Okay. So
Here
course,
updating W2 means this is
the derivative.
This is the eta.
Derivative. Not the eta. Yes. Eta is the learning rate. This is the derivative value. You will use this in the gradient descent update rule. Okay.
So are we done, by the way?
Like for the W2 we are done, then you can go with the W1. Last thing that I'm going to write is some sort of equation for the back. Okay, so the last thing that we are going to do is we are going to write some sort of equation for the back propagation. With that, we are done with the week 2 theory.
Sir, what do we call this sequence? Is this a one forward pass or what do we call it?
It's the backward path equation that I'm going to write. Okay. So we have like
sir, like using this like dl by dw2. Using this equation, we will be able to update with the help of gradient descent this equation.
Yeah.
Right. Okay.
Okay, so first equation was for the outer layer. Okay, so that is, if you are at the outer layer and you are taking the derivative of the loss function with respect to ZL, it was just simply y hat minus y. Okay. Now for updating the weights, okay, in any ith layer, if you are okay, then it's the derivative of the loss function.
In the outermost layer.
Yeah, in the outermost layer, but I want to generalize this. So if you look at here, this equation also, I can squeeze in it into what till now here.
This is the error from the previous part.
Yeah, so this red box is basically what? Derivative of loss function with respect to Z2.
Z2.
Okay, and we are multiplying it with derivative of Z2 with respect to W2.
W2.
Okay, so if you look at for any ith layer weight, if I'm updating, it's the derivative of loss function with respect to that Zi layer. Okay, till that Zi I have to compute.
Do Z.
Zi times that Zi times
with respect to dot Wi.
Okay, so that's one compact equation. Now you can try doing it for the bias also. Okay, it's simple with the bias. It will be 1.
Like how bias is affecting the loss function.
Yeah, so not in the loss function, in the forward pass equation. See, for any Zi, it's simply Wi Ai minus 1 plus Bi. Okay, so we have only computed for the weight. You can try computing it for the bias also, because the bias derivative will be just 1. Okay, so what will happen in that case? It will not getting multiplied with any other quantity. It will be just this only, gradient of the loss function with respect to that Zi. Okay, so if you are calculating for B2, it will be just the derivative of the loss function with respect to Z2 itself. Because the second part will be just 1. Right?
Where will Bi will come?
See, in the forward pass equation, Zi is Wi times Ai minus 1 plus Bi, right? Okay. So if you are going with the backward pass, okay, let's suppose you want to update the B2 here. Okay.
Yeah.
So you have computed till A2, then the derivative of A2 with respect to Z2. So then the Z2 derivative with respect to B2. Okay. But now if you look at the forward pass equation, okay, if you take the derivative of Zi with respect to Bi for any layer, what it will be? Just 1, right? Okay. So think of it like you have this function y equal to 5x plus 2. Okay. X is your this Ai minus 1. Wi is your 5. Bi is your bias here. Okay. Now if I'm going to take the derivative of this y with respect to this bias term, that would be just 1, right? Because it is like in the form of mx plus c.
Yes.
If I take the derivative of y with respect to c, it's just 1. Okay. So that's why I said the derivative of the loss function with respect to bias will just squeeze into this quantity, derivative of loss function with respect to Zi. Okay.
So there won't be any effect like due to bias?
It will be getting affected, but it's just that it will just affect this much, derivative of loss function with respect to Zi. That much effect it will do. Okay.
I think very minute change will be there.
Yeah. Like it depends upon how much this quantity is getting affected later on. Okay.
Got it.
So like for example, in this way we can take out everything like DL by DB1 and everything. But like is this going to affect the gradient descent also?
No. Here we are just calculating the gradient part. Okay, we are not going with the update part yet. What you have calculated till now is the gradient.
Okay, only the gradient part. Okay.
Yeah. Now you are going to use this gradient, feed it into the gradient descent update rule to update the parameter.
Okay, so basically the backpropagation is the main important step in the upgradation, right?
Yes.
Or the update one.
Yeah.
Okay.
So I know that things are a little complicated because it involves a lot of math. Okay.
Maths is easy, but it's confusing. Maths is very easy.
So see, I know understanding backpropagation in first go might not be easy. Even like I was also not able to get it in the first flow. So try practicing this just with this network. Okay, maybe 2-3 times. If you are just going to compute these equations by yourself. Okay, if you want it to be get verified, you can post it to your solution on the discourse. Okay, and you can tag me or Puneet. Okay, we will verify it for you whether the equations that you have got for each and every part is correct or not.
Sure, sir.
Try doing it 3-4 times with yourself. You will surely. And the main and good idea for to do the backpropagation is always remember how the forward equations are getting placed. Remember or just view the network structure, how the forward pass is getting happen. Okay, how the forward pass is getting happen. Just you have to do the reverse of that.
Yeah.
Okay, and you will be able to do it.
Sure.
So just try doing it just for this simple network. Okay, because in the vectorized and the multiplication form, okay, we are just going to do the extension of whatever we are doing it in the scalar form with respect to a little bit tuning with the size and the shape to make it consistent. Otherwise, once you are able to get it in the scalar form, you will surely able to adapt it to the vectorized form also. So that's why start with this simple network. Try doing it 3-4 times. If you have any doubt, you can post it on the discourse. We will review your equation there.
Sir, where can we get the recording, session recording and all? The previous and this lectures.
Session recordings are updated in Google Calendar. Okay, as soon as I am going to end
So
the
the
session.
access is not updated in some of the videos, sir.
For the last session that was taken by that was not given, but it is given now for that one.
So in my calendar.
Video give a public, not a private.
Yeah, but now it is given, na?
Yes, so now it's public. Now it's public. Now we can see.
Yeah, it was not public before, but now we have made it public. Don't worry. And for this also, after 2-3 hours, the recording will processed and get available.
So which calendar you are talking about? Like Google Calendar or like?
Google Calendar.
So in Google Calendar, I cannot see. I can only see that this we have like a session on this that date.
Not now because currently the recording is running, na? So
but like even if it's yeah.
As I am going to stop the recording, it will take 2 or 3 hours to process this recording. Then it will automatically get updated in the calendar event. Okay, so if I show it like, okay, so we have this here. Okay, here, okay, not in this. Maybe if I take an example of somewhere what happened.
So previous day, 26th, you check it's there.
Yeah. Okay. So like it will show it here. Okay, it will automatically get updated here.
Oh.
Currently it won't show. Okay, currently it will just give you this info. Later on it will get updated. Okay.
Okay.
So last session's recording, I want to say.
It is updated now. It was not given the access before, but now it's available.
No, last session means last TA session.
Sunday.
That recording is also available here. The notebook is also there. The recording is also there.
It's updated, sir.
Yeah.
Just a minute, sir. I'll see. Oh yes, sir. Now it's updated. Yes.
Okay.
Thank you, sir.
Thank you very much, sir, for the lecture, sir. Great lecture. Thank you.
Yeah, thank you.
Yes.
Thanks,
So
Dr.
the whole Wip2 theory part is covered, right?
Yes. Okay, no. One main thing was there, that was the XOR problem. Okay. Like how you resolve the XOR problem, because it is a non-linearly separable. That part is not there. Okay. You can look at the lecture to understand it. It's not very hard as of now if you understand everything, whatever we have covered. Except that only the implementation part is remaining. That we will do it in the next session tomorrow.
So like we have done up till the backward like the update part will be there in the week 3 or what? Like the updating part.
Upgrade is just you can use it to upgrade now. So you know
Or using the formula.
Yeah, just now how to take the derivative.
Yeah.
Once you have the derivative, you can just feed that into the gradient descent update rule to update your parameters.
Or we can use any form, the SGD or the mini batch.
Yeah, you can use anything. But for now, to learn things, try using SGD only.
Okay.
Because in that case, calculation will be simpler. So as I said, to understand the backpropagation, the small network that I have taken, okay, try 3-4 times on this to write down those equations. Okay, if you want it to be get verified, you can post it on the Discord. We will verify it for you. Okay, then you will be able to do it. Okay.
So one more question, like the one you use for your Mac version to write the notes, which it's a free version or you have paid for that?
I am using GoodNotes. I'm not sure whether it has the free version, but I am using the paid version for this.
Okay. Thanks, sir. Thank you, sir.
Yeah. Any more doubts, anyone? Okay, then I'm stopping the recording.